In the spring of 2019, a number appeared on a whiteboard at the Space Telescope Science Institute in Baltimore, Maryland. The number was 74.03. It had been refined over years of painstaking work, checked against multiple data sets, cross-verified by some of the most careful astronomers on Earth. It represented the speed at which the universe is flying apart, the Hubble constant, the heartbeat of cosmology, the single number that encodes how fast the space between galaxies is stretching. 74.03 kilometers per second per megaparsec. Write it down. Remember it. That number is half of the strangest crisis in modern physics. Now travel with me to a satellite. The Planck spacecraft finished its mission in 2013, having spent 4 years drifting at a gravitationally stable point 1,000,000 miles from Earth, staring at the oldest light in existence. That light, the cosmic microwave background, is the afterglow of the Big Bang, a faint thermal whisper that fills every cubic centimetre of space. Planck measured it with unprecedented precision. From those measurements, physicists could reconstruct the entire history of the universe: how much dark matter, how much dark energy, how much ordinary matter, how fast it expanded. And when they calculated what the Hubble constant should be today, derived not from nearby measurements but from the conditions at the beginning of time, they got a different number: 67.4. Stop and feel the weight of that. 74 versus 67. Two measurements of the same quantity. Two gold standard techniques, both pushed to exquisite precision, both checked and rechecked by independent teams, both published in the most prestigious journals in physics, and they do not agree. If you are comfortable with uncertainty, you might shrug. Measurements differ all the time. Error bars exist. Science is messy. But here is where the problem becomes strange. The error bars on both measurements have been shrinking for 20 years, and the numbers are not converging. They are diverging. The more carefully we measure, the worse the disagreement gets. In statistical terms, the gap between these two numbers now stands at more than 8 standard deviations from zero. That is not a wobble. That is not noise. That is two instruments, two methods, two independent lines of evidence, calmly and precisely insisting that they are measuring different universes. The technical name for this crisis is the Hubble tension. But tension is too gentle a word for what is happening. What we are witnessing is a slow-motion rupture in the foundations of cosmology, the field that tries to answer the largest question a mind can ask. What is the universe, and how does it work? For nearly a century, cosmology has been building a model of reality called lambda CDM, shorthand for a universe dominated by dark energy, lambda, and cold dark matter, CDM. That model has been spectacularly successful. It predicted the fluctuations in the cosmic microwave background before they were measured. It explained the large-scale structure of galaxy clusters. It told us the universe was flat, expanding, and accelerating. Lambda CDM became the standard model of cosmology for good reason. It worked. And now, quietly, it appears to be breaking. Over the next 2 hours, we're going to follow this crisis from its earliest hints to its current state of unresolved emergency. We will meet the astronomers who discovered the disagreement, the theorists scrambling to explain it, and the instruments, both earthbound and orbital, that keep making the problem worse by being more accurate. We will explore what it would mean if dark energy is not constant but changing. We will ask what new physics might be hiding in the gap between those two numbers, and we will confront a possibility that some cosmologists are not yet willing to say out loud, that our entire model of the universe, the model that explained everything from the Big Bang to today, may be wrong in a way we do not yet understand. If this kind of slow journey through the deep strangeness of reality is your thing, consider tapping that like and subscribe button. These long-form deep dives take months to research, and every subscription helps. Now, let us begin. To understand why 74 and 67 cannot both be right, you first have to understand what the Hubble constant actually measures. And to understand that, you have to understand that the universe is not sitting still. It never has been. Picture a loaf of raisin bread rising in an oven. Before you bake it, the dough is dense. The raisins are close together. But as the dough expands, every raisin moves away from every other raisin. A raisin near the centre sees its neighbours drifting away in all directions. A raisin near the edge sees the same thing. There is no centre to the expansion. Every point in the doze sees itself as the middle, and every other point receding. The universe works the same way. Space itself is the dough, galaxies are the raisins, and the universe has been rising, expanding, for 13.8 billion years. This expansion was discovered in the 1920s by an astronomer named Edwin Hubble. Working at the Mount Wilson Observatory in Southern California, Hubble was studying faint smudges of light that astronomers called nebulae. Some of these nebulae, it turned out, were not clouds of gas inside our own galaxy. They were entire galaxies in their own right. Island universes millions of light years away, each containing hundreds of billions of stars. Hubble noticed something peculiar. When he measured the light from these distant galaxies, the spectral lines, the fingerprints of specific atoms, were shifted toward the red end of the spectrum. This redshift, he realized, was a Doppler effect. The galaxies were moving away from us. Not just some of them, all of them, and the farther away a galaxy was, the faster it was receding. This relationship, distance proportional to velocity, is Hubble's law, and the constant of proportionality, the number that tells you how much faster a galaxy recedes for every additional megaparsec of distance, is the Hubble constant. Measure how fast a galaxy at a known distance is moving away, and you can calculate that constant. Or work backward. If you know the constant, you can use a galaxy's redshift to estimate its distance. For nearly a century, astronomers have been refining this measurement. The original value Hubble calculated in 1929 was wildly off, around 500 kilometers per second per megaparsec, because his distance estimates were crude. By the 1970s, the number had dropped to somewhere between 50 and 100. By the 1990s, it had narrowed to a range between 65 and 80. By the 2010s, it seemed to be converging on a single value, somewhere in the low 70s, and then the convergence stopped. To understand why, you have to understand that there are two completely different ways to measure the Hubble constant, and they rely on utterly different physics. The first method is what cosmologists call the distance ladder. It is exactly what it sounds like, a sequence of techniques, each one building on the last, that allows astronomers to measure distances to galaxies farther and farther away. You cannot measure the distance to a galaxy 100 million light-years away directly, but you can measure the distance to something closer, and use that to calibrate the next step, and use that to calibrate the step after that. The first rung of the ladder is parallax, the apparent shift in a star's position against the background sky as Earth orbits the Sun. If you measure that shift precisely, you can calculate the star's distance using simple trigonometry. But parallax only works for stars relatively close to us, within a few thousand light years. Beyond that, the shift becomes too small to measure. So astronomers use a different technique, standard candles. A standard candle is an astronomical object whose intrinsic brightness is known. If you know how bright something really is, and you measure how bright it appears, the difference tells you how far away it is. Light fades with distance according to the inverse square law. A candle twice as far away appears 4 times dimmer. A candle 100 times farther away appears 10,000 times dimmer. Measure the apparent brightness. Compare it to the known intrinsic brightness, and you have a distance. The most important standard candles in modern cosmology are Cepheid variable stars. Cepheids are giant pulsating stars, stars that swell and contract rhythmically, brightening and dimming as they do. In 1908, an astronomer named Henrietta Leavitt discovered something remarkable about them. She was studying Cepheids in the Small Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere. Because all the stars in that cloud are roughly the same distance from us, any differences in their apparent brightness must reflect differences in their intrinsic brightness. Leavitt found that the brighter a Cepheid was, the longer its pulsation period. A Cepheid that pulsed every 30 days was intrinsically brighter than one that pulsed every 10 days. This period-luminosity relationship was revolutionary. It meant that if you could measure how long a Cepheid took to pulse, you could calculate its intrinsic brightness. Compare that to its apparent brightness, and you had its distance. Suddenly, astronomers had a ruler they could use to measure distances far beyond the reach of parallax. The distance ladder works by chaining these techniques together. You use parallax to measure the distance to nearby Cepheids. You use those Cepheids to calibrate the period-luminosity relationship. You use that relationship to measure distances to Cepheids in other galaxies. And then you use those galaxies to calibrate an even brighter standard candle, type Ia supernovae. Type Ia supernovae are the catastrophic thermonuclear explosions of white dwarf stars. Under certain conditions, a white dwarf accumulates enough mass from a companion star to push it over a critical threshold, about 1.4 times the mass of our Sun, a limit called the Chandrasekhar mass. At that point, the star cannot support itself against gravitational collapse. The core compresses, heats up and detonates in a runaway fusion reaction that destroys the star entirely. The explosion is so bright it can briefly outshine the entire galaxy that hosts it. Because this explosion is triggered by a mass threshold, all type A supernovae are roughly the same brightness. They are not perfect standard candles. There are small variations, and astronomers have developed sophisticated techniques to correct for them, but they are good enough, and they are bright enough to be seen across billions of light years, far beyond the reach of Cepheids. So the distance ladder runs like this: parallax to nearby Cepheids, Cepheids to nearby galaxies to calibrate type Ia supernovae to the distant universe. At each rung you measure distances. You also measure redshifts, how fast those galaxies are receding. Combine distance and redshift and you get the Hubble constant. This is the method that produced 74.03. The measurement was led by Adam Rees at Johns Hopkins University and the Space Telescope Science Institute, using data from the Hubble Space Telescope. Rees and his team have been refining this measurement for over 2 decades. They have calibrated their Cepheids against the best parallax measurements available. They have corrected for systematic errors in every way they can imagine. They have subjected their analysis to the most rigorous scrutiny in the field. 74.03 is not a rough estimate. It is one of the most carefully measured numbers in all of astronomy, and it is completely incompatible with 67.4. The second method for measuring the Hubble constant does not use the distance ladder at all. It does not look at nearby galaxies, or Cepheids, or supernovae. Instead, it looks at the oldest light in the universe, the cosmic microwave background, and works backward. To understand this, you have to understand what the cosmic microwave background actually is. The universe began in a hot, dense state, the Big Bang, roughly 13.8 billion years ago. In the earliest moments, space was so hot that atoms could not form. Electrons flew freely, colliding constantly with photons, scattering light in every direction. The universe was opaque, a seething fog of plasma. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped enough for electrons to bind with protons, forming neutral hydrogen atoms. Suddenly photons could travel freely without being scattered. The fog lifted. Light poured out in every direction, the first light that could cross the universe unimpeded. That light has been travelling ever since. For 13.8 billion years it has crossed the expanding cosmos, its wavelength stretching as space itself stretched. What began as visible light, the glow of a hot plasma, has redshifted into the microwave range. Today it fills all of space, coming from every direction, with a temperature of about 2.7 degrees above absolute zero. This is the cosmic microwave background, the CMB, the afterglow of the Big Bang. The CMB is not perfectly uniform. It has tiny fluctuations, variations in temperature of about 1 part in 100,000. These fluctuations are fossils. They record the density variations in the early universe, the seeds from which galaxies would later grow. By mapping these fluctuations precisely, physicists can reconstruct the conditions at the moment the light was released, 380,000 years after the Big Bang. The Planck satellite was designed to make the most precise map of the CMB ever created. It measured the temperature of the microwave sky at multiple frequencies, filtering out contamination from our own galaxy and from distant sources. The result was a nearly perfect picture of the infant universe, a map of the primordial fluctuations with unprecedented resolution. But Planck did more than just make a picture. It used that picture to constrain the parameters of our cosmological model. By fitting the pattern of fluctuations to theoretical predictions, physicists could determine how much dark matter the universe contains, how much ordinary matter, how much dark energy, and how fast the universe was expanding at that early moment. And if you know the expansion rate at an early time, and you know how the universe has been expanding since then, which is predicted by the standard model of cosmology, you can calculate what the expansion rate should be today. That calculation gives 67.4. Let me put that in perspective. The distance ladder measures the Hubble constant directly, in the present-day universe, using distances and redshifts to nearby and moderately distant galaxies. Planck measures the Hubble constant indirectly, by looking at the infant universe and running the clock forward using our best model of how the cosmos evolves. These are two completely independent methods. They rely on different observations, different physics, different techniques. In principle, they should give the same answer. They do not. The first hints of disagreement appeared over a decade ago, but they were easy to dismiss. Error bars were large. The measurements were converging slowly. It seemed like normal science, different groups refining their techniques, getting closer to the true value with each passing year. But something strange happened around 2016. The error bars kept shrinking, and the numbers did not converge. The distance ladder measurement got more precise, settling more firmly in the low 70s. The Planck measurement got more precise, settling more firmly in the high 60s. The gap between them did not close. It widened in statistical significance, if not in absolute terms. Let me explain what that means. In statistics, you measure disagreement in terms of standard deviations, a way of quantifying how likely it is that two measurements differ by chance alone. One standard deviation is common. 2 standard deviations is unusual but not alarming. 3 standard deviations, often called the 3 sigma threshold, is where physicists start to take notice. 5 sigma is the gold standard for claiming a discovery in particle physics. It means the odds of the result being a fluke are less than 1 in 3.5 million. The Hubble tension is now above 8 sigma. Stop and feel the weight of that. 8 sigma means the probability that this disagreement is due to random chance is vanishingly small. Less than 1 in 100 trillion. Something is wrong. Either one of the measurements has a systematic error that no one has found, or both measurements are correct and our model of the universe is missing something fundamental. The astronomers and physicists working on this problem have spent years hunting for systematic errors. Every conceivable source of bias has been examined, quantified, and corrected for. The Cepheid calibration has been checked against independent distance indicators. The supernova light curves have been analysed with different techniques. The Planck data has been reprocessed, recalibrated, and cross-checked against other CMB experiments. Nothing has closed the gap. In fact, the gap has been confirmed by independent measurements on both sides. On the distance ladder side, other techniques have been developed that bypass Cepheids entirely. One uses the tip of the red giant branch, a sharp cut-off in the brightness of old red giant stars that serves as another standard candle. Another uses mirror variable stars, a different class of pulsating giants. Another uses water masers, natural microwave lasers in the accretion disks around supermassive black holes, which can be used for exquisitely precise geometric distance measurements. All of these methods give values in the low to mid-70s. Not all agree perfectly with each other, but they cluster around 73 to 74. None of them agree with Planck. On the CMB side, ground-based experiments like the Atacama Cosmology Telescope and the South Pole Telescope have made independent measurements of the microwave background. Their results are consistent with Planck. 67, give or take, not 74. 2 families of measurements, 2 different answers, both getting more precise, neither budging. Here is where we have to confront what this disagreement actually implies. If the distance ladder measurements are correct, and the universe really is expanding at 74 kilometers per second per megaparsec, then something is wrong with the way we extrapolate from the early universe to the present day. The Planck measurement assumes we know exactly how the universe has expanded over the last 13.8 billion years. It assumes the standard model of cosmology, lambda CDM, is correct. Dark energy is a cosmological constant, unchanging over time. Dark matter is cold and weakly interacting. The curvature of space is flat. Neutrinos have tiny masses. General relativity works on cosmological scales. If 74 is the true value, at least one of those assumptions is wrong. The most exciting possibility, the one that has theorists scrambling to publish papers, is that dark energy is not constant. In the standard model, dark energy is represented by lambda, the cosmological constant, a fixed amount of energy built into the fabric of space itself. It drives the accelerating expansion of the universe, pushing galaxies apart faster and faster. But what if lambda is not constant? What if dark energy evolves over time, changing its strength as the universe ages. This is not a new idea. Physicists have long wondered whether dark energy might be a dynamic field rather than a fixed constant. They have given it names like quintessence, after the fifth element of ancient philosophy. In quintessence models, dark energy can vary, sometimes stronger, sometimes weaker, depending on conditions in the universe. If dark energy were stronger in the early universe and weaker now, it would change the relationship between the infant cosmos and the present day. The Planck extrapolation would be off. The true Hubble constant would be higher than Planck predicts. But there is a problem. Changing dark energy does not just affect the Hubble constant. It affects everything else Planck measures too: the pattern of fluctuations in the CMB, the growth of cosmic structure, the timing of key events in cosmic history. And so far, no model of evolving dark energy has been able to resolve the Hubble tension without creating new tensions elsewhere. The models that fix the Hubble constant tend to break the CMB fit. The models that preserve the CMB fit tend to leave the Hubble constant unchanged. It is like trying to push a dent out of a car fender. You fix one spot, and the metal bulges somewhere else. Another possibility is that there is new physics in the early universe, something that happened before the CMB was released, something that changed the expansion rate in those first few 100,000 years. One idea is called early dark energy, a brief pulse of extra energy density in the young cosmos, which would have caused the universe to expand slightly faster, then faded away. This would change the sound horizon, the characteristic distance scale imprinted in the CMB fluctuations, in a way that shifts the inferred Hubble constant upward. Early dark energy models are promising, but they face challenges of their own. They require fine-tuning. They introduce new parameters that must be adjusted just so, and they do not yet fit all the data perfectly. The CMB is not the only window into the early universe. Measurements of the cosmic baryon acoustic oscillations, the ripples in the distribution of galaxies, echoing those primordial density waves, provide independent constraints. Early dark energy models struggle to match both the CMB and the BAO data simultaneously. Some theorists have proposed modifications to the properties of neutrinos, those ghostly particles that barely interact with ordinary matter. Neutrinos are weird. They oscillate between different types as they travel. They have mass, but we do not know how much. In the standard cosmological model, the sum of all neutrino masses is assumed to be very small. But what if it is larger? Or what if there are additional neutrino species we have not detected? Or what if neutrinos have exotic properties, interactions with dark matter, or unusual relativistic effects in the early universe? These ideas are being tested. So far, none of them have solved the puzzle. And then there is the most mundane possibility, the one that every careful scientist must consider, that someone is making a mistake. Somewhere, in one of the measurements, there is a systematic error that has escaped detection, a calibration that is slightly off, a selection effect that biases the sample, a model assumption that does not hold, a piece of physics that contaminates the signal. The teams working on both sides of this problem are acutely aware of this possibility. They have been looking for systematic errors for years. The distance ladder measurements have been checked by multiple independent groups using different techniques. The CMB measurements have been cross-validated by different experiments. If there is a hidden systematic, it is hidden extraordinarily well. The troubling thing is that systematic errors are, by definition, the errors you do not know about. You can check for all the systematics you can think of, but you cannot check for the ones you have not thought of. This is the dark underbelly of precision measurement. The more precise your result, the more vulnerable you are to unknown unknowns. Imagine you are a cosmologist in the year 2000. The standard model of cosmology is coming together beautifully. Dark matter explains the rotation curves of galaxies and the growth of cosmic structure. Dark energy explains the accelerating expansion discovered just 2 years earlier. The CMB fluctuations match the theoretical predictions with remarkable accuracy. Lambda CDM is elegant, parsimonious, and apparently correct. The Hubble constant is still being debated. Values range from 60-something to 70-something, but the debate's a normal science. Error bars are large. Resolution seems imminent. Now imagine you are that same cosmologist in 2024. The error bars have collapsed. The instruments have improved beyond anything you could have imagined. Planck has mapped the CMB to exquisite precision. The Hubble Space Telescope has measured key feeds in dozens of galaxies. James Webb is coming online, promising even sharper observations. and the numbers are not converging, they are pulling apart. The two most reliable ways of measuring the expansion rate of the universe are giving incompatible answers, and the disagreement is now so large that it cannot be explained by chance. This is the Hubble tension. This is the crisis. There is something almost uncanny about this moment in cosmology. For most of history, scientists have been limited by the crudeness of their instruments. They made the best measurements they could, knowing that better measurements would come later. They expected precision to bring clarity. They expected that as error bar shrank, nature would reveal herself, her true values emerging from the fog of uncertainty like a photograph developing in a dark room. But here, precision has brought the opposite. The more carefully we look, the more confusing the universe becomes. It is as if nature is punishing us for our diligence, for our ambition to measure her to the 15th decimal place. The numbers are not converging. They are diverging, and the universe is not explaining why. Let that settle for a moment. The Hubble tension is not a puzzle to be solved with a clever calculation. It is a warning. It is telling us that something we believe about the cosmos, something we have believed for decades, is wrong. We do not know what. We do not know how to find out. All we know is that when we measure the universe two different ways, we get two different answers, and the answers are not converging. In the chapters ahead, we will trace the history of these measurements, how the distance ladder was built rung by rung, how the CMB became a precision tool, how the disagreement emerged and hardened. We will meet the scientists on the front lines of this crisis, fighting over calibration constants and selection effects and theoretical models. We will explore the possibilities, evolving dark energy, early dark energy, new particles, modified gravity, systematic errors too clever to find, and we will ask a question that has no answer yet. What does it mean if the universe is measuring itself differently than we expected? What does it mean if the heartbeat of the cosmos, the Hubble constant, the number that tells us how fast reality is flying apart, is not a single number at all, but a discordance, a dissonance, a tension that refuses to resolve? The crisis is not over. It is just beginning. The city of Leiden in the Netherlands is an unlikely place for a revolution in our understanding of the cosmos. It is a medieval city, threaded with canals, home to one of the oldest universities in Europe. The architecture is brick and stone, weathered by centuries of rain. Students cycle along cobblestone streets past churches that were old when Galileo was young. In the physics department, behind thick walls that keep out the Dutch winter, researchers have been quietly assembling evidence that the universe is stranger than anyone expected. One of those researchers is Henk Hoekstra, a cosmologist who specialises in weak gravitational lensing, the subtle distortion of distant galaxy images caused by the gravitational pull of intervening matter. It is a technique that allows astronomers to map the distribution of dark matter in the universe, and it provides yet another window into the cosmological parameters that govern cosmic expansion. Hoekstra is one of the scientists who has spent years trying to reconcile different measurements of the universe. He knows the Hubble tension intimately. He has seen papers proposing solutions rise and fall, seen promising ideas founder on new data, seen the disagreement persist year after year, despite the best efforts of some of the smartest people on Earth. When you ask him what he thinks is happening, he pauses. He chooses his words carefully. He says that he does not know. He says that no one knows. He says that the tension is real, the measurements are solid, and something has to give. What that something is, whether it is a systematic error or new physics or something no one has imagined yet, remains to be seen. This is the honest state of cosmology in the mid-2020s. The field is in crisis, but it is a productive crisis. Papers are being published, models are being tested, new observations are being planned. The James Webb Space Telescope is already returning data that will sharpen the distance ladder measurements. The Euclid mission, launched in 2023, will map the cosmic web with unprecedented precision, providing new constraints on dark energy and cosmic structure. The Vera C. Rubin Observatory, under construction in Chile, will survey the southern sky with a 10 billion pixel camera, discovering millions of supernovae and galaxies over the next decade. All of this data will bear on the Hubble tension. All of it will either confirm the disagreement or reveal the error that resolves it. But as of now, in this moment, we do not know which outcome awaits us. We do not know if we are on the verge of discovering new physics or uncovering a systematic mistake. We do not know if the standard model of cosmology will survive or crumble. What we know is that two numbers, 74 and 67, are both precisely measured and mutually incompatible. We know that the universe is expanding, that space itself is stretching between the galaxies, that the cosmos is flying apart at a rate we can measure but apparently cannot agree upon. We know that either our observations are flawed, or our model is incomplete, or the universe is more complex than we thought. And we know that this tension, this quiet catastrophe in the heart of cosmology, has not been resolved. The crisis continues. Let me take you inside one of those measurements. Not the summary, not the number at the end of the paper, but the actual chain of reasoning that produces it. Because the Hubble tension is not a disagreement between two scientists or two research groups. It is a disagreement between two entire methodologies, two completely independent ways of interrogating the universe, each one built on decades of refinement, each one checked and rechecked until the uncertainties have been squeezed down to almost nothing. To understand why this disagreement is so unsettling, you need to feel the weight of the chains. Start with the distance ladder. The phrase itself is almost whimsical. It suggests something rickety, something improvised. Rungs nailed together by astronomers desperate to climb out of their cosmic well and see how far things really are. But the metaphor is misleading. The modern distance ladder is not rickety. It is one of the most carefully constructed measurement systems in all of science. Each rung has been tested against the others, cross-checked using multiple techniques, calibrated with data from space telescopes and ground observatories, and decades of patient observation. The astronomers who build distance ladders are not guessing. They are triangulating, using geometry and physics, and the predictable behaviour of certain kinds of stars to leap from the nearby to the impossibly far. The first rung is parallax. This is pure geometry, the same principle you use when you close one eye and then the other, and watch nearby objects shift against the background. Hold your thumb in front of your face and alternate eyes. Your thumb jumps. That jump is parallax. Now do the same thing with the Earth. In January, the Earth is on one side of its orbit around the Sun. In July, it is on the other side, 300 million kilometres away. A nearby star, observed in January and July, will appear to shift against the backdrop of more distant stars. That shift is tiny. Fractions of an arc-second, angles so small that the human eye cannot detect them, but space telescopes can. The Gaia satellite, launched by the European Space Agency, has measured the parallax of more than 1 billion stars with astonishing precision. For nearby stars within a few thousand light-years, these distances are now known to within a fraction of a percent. But parallax only works for relatively nearby stars. Beyond a few tens of thousands of light-years, the shift becomes too small to measure, even for Gaia. You need another rung. This is where Cepheid variables enter the story. Cepheids are giant pulsating stars, bloated spheres of gas that breathe in and out on timescales of days to weeks. They swell and shrink, brighten and dim, in a rhythm as regular as a cosmic metronome. And here is the crucial fact. The period of that pulsation, how many days it takes for a Cepheid to complete one cycle of brightening and dimming, is directly related to its intrinsic luminosity. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. This relationship was discovered by Henrietta Swan Leavitt in 1912, working at the Harvard College Observatory, analysing photographic plates of stars in the Small Magellanic Cloud. She was paid 30 cents an hour. She was classified as a human computer, not an astronomer. And she handed humanity one of the most powerful tools in the history of cosmology. The period luminosity relation means that if you measure a Cepheid's pulsation period, you know its true brightness. Compare that to its apparent brightness, how dim it looks from Earth, and you can calculate its distance. The dimmer it looks compared to what it should be, the farther away it is. This is not an approximation. This is physics. Light spreads out as it travels. The relationship between true brightness, apparent brightness, and distance is a mathematical certainty. Astronomers have calibrated the period luminosity relation using Cepheids whose distances are known from parallax. Gaia has measured parallaxes for thousands of Cepheids in our own galaxy. Those measurements anchor the relation, allowing astronomers to use Cepheids as standard candles out to distances of tens of millions of light-years, far enough to reach nearby galaxies where parallax is useless, but Cepheids still pulse with their telltale rhythm. Already you can feel the chain linking. Parallax tells us the distances to nearby Cepheids. The period luminosity relation lets us use those Cepheids to calibrate the brightness scale. With that scale in hand, we can measure the distances to Cepheids in other galaxies, and those distances let us calibrate the next rung, type Ia supernovae. Type Ia supernovae are the hydrogen bombs of the cosmos. They occur when a white dwarf star, a dense Earth-sized remnant of a sun-like star, accumulates matter from a companion until it crosses a critical mass threshold. At that point, the entire star detonates in a thermonuclear explosion so bright it briefly outshines its entire host galaxy. For a few weeks, a single dying star produces more light than 100 billion suns, and because white dwarfs detonate at roughly the same mass, a threshold set by the fundamental physics of degenerate matter, type Ia supernovae, have roughly the same intrinsic brightness. Not exactly the same. There is variation, but that variation is correlated with how quickly the supernova fades after peak brightness. A type Ia that fades slowly is intrinsically brighter. A type Ia that fades quickly is intrinsically dimmer. Correct for the fade rate, and you have a standard candle that can be seen across the universe. Supernovae visible in galaxies where Cepheids have already been measured anchor the calibration. If you know the distance to a galaxy from its Cepheids, and you observe a type Ia supernova in that same galaxy, you know the supernova's intrinsic brightness. Now you can look for type Ia supernovae in galaxies so far away that no individual stars can be resolved, not even pulsating Cepheids, and use the supernova's brightness to calculate the distance. This chain, parallax to Cepheids to supernovae, is the distance ladder. Each rung depends on the one below it. If any rung is miscalibrated, the entire ladder shifts. And at the top of the ladder sits the Hubble constant. Here is how you get from distances to expansion rate. Edwin Hubble's original discovery was that galaxies are moving away from us, and the farther away they are, the faster they recede. That recession is not motion through space in the ordinary sense. It is the stretching of space itself, carrying galaxies along like raisins in rising bread. Measure the redshift of a galaxy, the stretching of its light toward longer wavelengths, and you know how fast it is receding. Measure its distance using the distance ladder, and you have two numbers, velocity and distance. Divide velocity by distance. The answer is the Hubble constant. In principle, this is simple. In practice, it is extraordinarily difficult. Galaxies do not just recede due to cosmic expansion. They also have their own peculiar motions, gravitational tugs from nearby matter, infall toward clusters, random movements through the cosmic web. These peculiar velocities contaminate the signal. To get a clean measurement of cosmic expansion, you need to look at galaxies far enough away that their recessional velocity due to expansion dwarfs their peculiar motions. But the farther away you look, the harder it is to measure distances precisely. This is the bind the distance ladder astronomers find themselves in. They need nearby measurements to calibrate their standard candles, but they need distant measurements to isolate the expansion signal. The entire enterprise is a balancing act, a chain of inferences stretching from the nearest stars to the farthest galaxies, each link forged with care, each link a potential source of error, and yet, remarkably, the chain holds. Different research groups using slightly different methods, different Cepheid catalogues, different supernova samples, different calibration techniques, arrive at consistent answers. The Schwess team, led by Adam Rees at Johns Hopkins University, has spent nearly 2 decades refining this measurement. Their latest value, published in 2022, is 73.04 km per second per megaparsec, with an uncertainty of just over 1%. Other teams, using similar methods, find similar values. The distance ladder, for all its complexity, produces a consistent answer. That answer is 73, not 67, 73. Now travel backward in time, not with a telescope but with mathematics. Leave the distance ladder behind and consider an entirely different way of measuring the universe. The cosmic microwave background is the afterglow of the Big Bang. It is the oldest light in existence, released 380,000 years after the beginning of everything, when the universe cooled enough for electrons and protons to combine into neutral hydrogen and light, was finally free to travel without being scattered. That light has been travelling ever since, stretched by the expansion of space from visible wavelengths to microwaves, carrying information about the infant universe across 13.8 billion years. When you look at the cosmic microwave background, you're looking at a snapshot of the universe when it was less than a millionth of its current age. It is not a photograph in any ordinary sense. It is a map of temperature fluctuations, tiny variations, 1 part in 100,000, in the intensity of the background radiation. Some patches are slightly warmer, some are slightly cooler. These fluctuations trace the density variations in the early universe, the seeds that would eventually grow into galaxies and clusters and the cosmic web we observe today. The pattern of those fluctuations is not random. It has structure. It has peaks and troughs at characteristic scales, set by the physics of sound waves in the early universe. Yes, sound waves. In the dense, hot plasma before recombination, photons and matter were coupled together, and pressure waves, acoustic oscillations, propagated through the medium. Those waves left imprints in the density of matter, and those imprints froze in when the universe cooled and the photons decoupled. The pattern of peaks in the cosmic microwave background tells us the size of those acoustic oscillations at the moment of recombination. And because we know the physics of the early universe extremely well, the temperature, the density, the speed of sound in the primordial plasma, we can calculate what size those oscillations should have been. Here is the key. We know the physical size of the oscillations at recombination. We observe the angular size of the oscillations on the sky today, how many degrees across they appear. Compare the two, and you get the distance to the surface of last scattering. The distance light has travelled since the cosmic microwave background was released. Now add one more ingredient. We know the age of the universe at recombination, 380,000 years, from the physics of the early universe. We know the age of the universe today, 13.8 billion years, from the same physics, calibrated by the expansion history. The Hubble constant connects distance and expansion rate. If we know the distance to the cosmic microwave background and the age of the universe, we can infer how fast the universe has been expanding. This is not a direct measurement of nearby galaxies. This is a reconstruction, a backward inference from the early universe to the present day, using a model, the Standard Cosmological Model, LCDM, that describes how the universe expands over time. The model assumes dark matter, dark energy with a constant density, and general relativity as the law of gravity. Given those assumptions, the cosmic microwave background data pins down the Hubble constant. The Planck satellite, which observed the cosmic microwave background with exquisite precision from 2009 to 2013, delivered a measurement that shook cosmology, 67.4 kilometers per second per megaparsec. Uncertainty, less than 1%, a result so precise that the statistical error bars were almost invisibly small. Stop and feel the weight of that. 2 measurements, each with uncertainties of roughly 1%, arriving at numbers that differ by 9%. If both measurements were correct, their error bars would overlap. They do not. They miss each other by 8 standard deviations, 8 sigma. In physics, 5 sigma is the threshold for a discovery. It means there is a 1 in 3 million chance that the result is a statistical fluke. 8 sigma is orders of magnitude more certain. The disagreement between the distance ladder and the cosmic microwave background is not a fluke. It is real. The first instinct when faced with such a disagreement is to look for a mistake. Perhaps the Cepheid calibration is off. Perhaps the supernova standardization is imperfect. Perhaps there is some unaccounted systematic error in the distance ladder, some subtle bias that nudges the measurement high. The US team has spent years hunting for such errors. They have varied their Cepheid sample, switching from one calibration anchor to another. They have used Cepheids in the Milky Way, Cepheids in the Large Magellanic Cloud, Cepheids in the nearby galaxy NGC 44258, whose distance is known from water mazes, a completely independent geometric technique. Every time they change the anchor, the Hubble constant stays stubbornly high, 72, 73, 74. The number refuses to budge. They have worried about crowding. The possibility that Cepheids in dense stellar environments appear brighter than they should because unresolved nearby stars contaminate the photometry. They have used the Hubble Space Telescope's sharpest instruments to minimize this effect. They have compared results from Hubble to results from the James Webb Space Telescope, which observes in the infrared where crowding is less severe. The answer stays the same, 73. They have worried about dust. Dust scatters and absorbs starlight, making stars appear dimmer and redder than they are. If the dust corrections are wrong, the Cepheid luminosities could be biased. But modern dust maps, calibrated with infrared observations, are precise. The corrections are well understood. The answer stays the same. They have worried about metallicity, the chemical composition of the Cepheids. Stars with more heavy elements behave slightly differently than stars with fewer. The period luminosity relation might depend on metallicity, but this effect has been measured and corrected for. The answer stays the same. Every potential systematic error has been investigated. Every plausible bias has been quantified. The error budget of the Shuri-S measurement is detailed and public, listing dozens of potential sources of uncertainty and their estimated contributions. Add them all up in quadrature, and the total uncertainty is 1.4%. The central value is still 73. Meanwhile, the Planck measurement has faced similar scrutiny from a different direction. The cosmic microwave background analysis depends on the cosmological model. If the model is wrong, if dark energy is not constant, if dark matter has unexpected properties, if the geometry of the universe is slightly different from what we assume, then the inferred Hubble constant could be off. But the Planck team has tested many variations. They have allowed the dark energy equation of state to vary. They have considered models with extra neutrino species. They have explored the possibility that the universe is not quite flat. In most of these variations, the Hubble constant shifts slightly, but not enough to resolve the tension. To bring the Planck value up to 73, you need changes so drastic that they conflict with other observations. Consider neutrinos. In the standard model, there are 3 species of neutrinos, lightweight particles that barely interact with ordinary matter. But physicists have speculated about additional sterile neutrinos that interact even less. Adding extra neutrino species to the cosmological model changes the expansion history of the early universe and can push the inferred Hubble constant higher. But the effect has limits. Too many extra neutrinos would leave imprints in the cosmic microwave background that we do not observe. You cannot add enough extra neutrinos to fully close the gap without conflicting with the data. Consider dark energy. The simplest model assumes that dark energy has a constant density, the cosmological constant L, that gives LCDM its name. But what if dark energy changes over time? What if it was denser in the past or less dense? Or what if it evolves in some complex way? Theorists have constructed models where dark energy increases with time, reducing the inferred Hubble constant from the cosmic microwave background. Other theorists have proposed the opposite. Dark energy, that was stronger in the early universe, accelerating expansion more than expected, and raising the inferred Hubble constant. None of these models fit all the data elegantly. Each one solves part of the puzzle while creating new tensions elsewhere. The honest summary is this. The Planck measurement assumes the standard model of cosmology, and if the standard model is correct, the Hubble constant is 67. But if the standard model is wrong, if something fundamental is missing, then the true Hubble constant could be different, and the Planck analysis would not capture that difference. This is the crux. The distance ladder measures the universe directly. Light from nearby stars reaches our telescopes. We see the Cepheids pulsating. We watch the supernovae brighten and fade. The physics is elementary. The inverse square law, the period luminosity relation, the behavior of thermonuclear explosions. The distance ladder is a chain of direct observations. The cosmic microwave background measurement is indirect. It infers the Hubble constant by fitting a model to the pattern of temperature fluctuations in ancient light. The model is the standard cosmological model, our best current description of how the universe evolves. If the model is correct, the inference is valid. If the model is incomplete, the inference could be biased. This asymmetry matters. Many cosmologists, when forced to bet, would say that if the disagreement is real, it is more likely that the model is wrong than that the distance ladder is wrong. The distance ladder is direct. The cosmic microwave background is model-dependent. New physics, if it exists, could hide in the gap. But this is not a consensus. Other cosmologists point out that the distance ladder has many rungs, each one a potential failure point. The cosmic microwave background analysis, while model-dependent, is based on physics we understand extremely well, the behavior of photons and baryons in the early universe. The standard model is not a guess. It is a framework that has passed hundreds of tests. To break it, you need something dramatic. Let me take you to another laboratory, another kind of measurement, another attempt to triangulate the truth. In Hawaii, on the summit of Mauna Kea, The twin domes of the Keck Observatory stand above the clouds. At 4,200 meters elevation, the air is thin and dry, the sky is dark, and the seeing, the steadiness of the atmosphere, is among the best on Earth. The Keck telescopes are giants, each one with a primary mirror 10 meters across, segmented into 36 hexagonal pieces that work together as a single light-collecting surface. Astronomers using Keck have pioneered a technique called time delay cosmography. It relies on a phenomenon Einstein predicted a century ago, the bending of light by gravity. When a massive object, a galaxy or a cluster, lies between us and a more distant source, the light from the source is deflected. If the alignment is right, we see multiple images of the source, bent around the intervening mass like reflections in a funhouse mirror. Sometimes the source is a quasar, a supermassive black hole swallowing matter at the centre of a distant galaxy, blazing with the light of 1 trillion suns. Quasars are variable. They flicker and flare as clumps of matter spiral into the black hole. If we see multiple images of a quasar bent around an intervening galaxy, we can watch the flickering in each image. But the images do not flicker in sync. One image has a shorter path through the gravitational lens. The other has a longer path. The light from one image arrives before the light from the other. The delay is days or weeks, depending on the geometry. Measure the time delay. Model the mass distribution of the lensing galaxy. Calculate the difference in path length. The difference in arrival time, combined with the difference in path length, tells you the absolute scale of the system, the distance to the lens and the source. And from distances, once again, you get the Hubble constant. This is an entirely independent method. It does not rely on Cepheists or supernovae. It does not assume the standard cosmological model. It is pure geometry, Einstein's geometry, the bending of space-time around massive objects. The Euler-Lecau collaboration, a whimsical acronym standing for Auro lenses in Cosmograil's wellspring, has spent years refining this technique. They have studied 6 lensed quasars with exquisite care, modelling the mass distributions of the lensing galaxies, measuring the time delays between images, accounting for every systematic uncertainty they can identify. Their result, 73.3 kilometers per second per megaparsec. Within the uncertainties, identical to the distance ladder. Another independent vote for 73. This is what makes the tension so troubling. It is not a disagreement between two measurements. It is a disagreement between two families of measurements. The distance ladder and time delay cosmography both probe the local universe, the universe as it exists today. They both give answers near 73. The cosmic microwave background probes the early universe, 13 billion years ago. It gives 67. The local universe and the early universe are measuring different values for the same constant, unless the constant is not constant. That possibility hangs in the air, unspoken in polite company, whispered in corridors at conferences. The Hubble constant is supposed to be constant, a fixed number that describes the current expansion rate of the universe. But what if the expansion rate itself is changing in ways the standard model does not capture? What if dark energy is evolving? What if the universe went through phases we do not understand, acceleration and deceleration in patterns more complex than our models predict? If that is true, if the expansion history is richer than we thought, then the Hubble constant is not a single number. It is a function, a curve, a history that varies across cosmic time. The value you measure depends on when you are measuring it, and the two methods, local and early, are sampling different epochs. This is speculation. There is no consensus model of evolving dark energy that fits all the data cleanly. But the possibility exists, lurking at the edge of the mainstream, a potential explanation for the 8 sigma tension. Let me give you another number to hold. This one comes not from telescopes but from theory, and it is the largest discrepancy in all of physics. When physicists calculate the energy of the quantum vacuum, the ground state of empty space, the roiling sea of virtual particles flickering in and out of existence, they get a number. When cosmologists measure the density of dark energy from the acceleration of the universe, they get a different number. The ratio between the two is 10 to the power of 120, not a discrepancy of 10% or a factor of 2, a discrepancy of 120 orders of magnitude. This is called the cosmological constant problem, and it has haunted physics for decades. No one knows how to resolve it. The standard response is to throw up one's hands and invoke the anthropic principle. Perhaps the vacuum energy takes different values in different regions of a vast multiverse, and we find ourselves in a region where the value is small enough for galaxies to form and life to evolve. Perhaps there is no deeper explanation. Perhaps we're just lucky. I mention this because it illustrates something important. Cosmology is not a finished science. Our models work. They predict the cosmic microwave background, the large-scale structure of galaxies, the abundance of light elements forged in the Big Bang, but they rest on foundations we do not fully understand. Dark energy is a name for our ignorance. Dark matter is a name for our ignorance. The Hubble constant is a measurement of something we cannot explain from first principles. The tension is a crack in a beautiful edifice. The edifice still stands, it still shelters us, gives us predictions that match observations, provides a framework for understanding the cosmos. But the crack is there, visible now, and it is not getting smaller. It is getting clearer as the measurements improve. Somewhere in that crack, new physics may be hiding, or somewhere in our instruments a subtle error may be waiting to be found. We do not yet know which. The measurements continue. The telescopes keep watching. The papers keep flowing. And the universe keeps expanding indifferent to our confusion, stretching the space between galaxies at a rate we can measure but cannot agree upon. That phrase, indifferent to our confusion, deserves a moment of its own, because the universe truly does not care whether we understand it. The cosmos is not a puzzle designed for human minds to solve. It is not a mystery novel with clues planted for clever detectives. It is simply what it is, unfolding according to laws we did not write and cannot revoke. Our confusion is our problem, not nature's. And yet, the confusion has a texture. It has a history. It involves real people in real rooms, staring at real data, making real decisions about what to trust and what to doubt. The Hubble tension is not just a disagreement between numbers. It is a disagreement between methods, between teams, between philosophies of how to approach the edge of knowledge. Behind every decimal place stands a human being who chose how to calibrate an instrument, which systematic errors to worry about, which assumptions to treat as safe. Let me take you into one of those rooms. The year is 2019. The place is a conference hall at the Kavli Institute for Theoretical Physics in Santa Barbara, California. The building sits on a bluff overlooking the Pacific Ocean, and through the windows the February sun casts long shadows across tables littered with coffee cups and laptops. This is not a typical astronomy conference. This is an intervention. The organisers have brought together the principal investigators of both camps, the distance ladder teams and the cosmic microwave background teams, along with theorists, statisticians, and a handful of independent voices whose job is to ask uncomfortable questions. The goal is simple: find the error. If there is an error in the local measurements, find it. If there is an error in the early universe measurements, find it. If both measurements are correct and the tension is real, say so clearly. But stop dancing around the problem. Stop publishing papers that frame the disagreement as intriguing or potentially interesting. Call it what it is: a crisis. The room is tense. Adam Rees is there, the man whose team has pushed the HRUS measurement to its current precision. He won the Nobel Prize for discovering the accelerating expansion of the universe. He knows what a cosmological revolution feels like. He also knows what it feels like to be told his measurements are wrong. Across the room sits George of Stathew, one of the architects of the Planck mission, a cosmologist who has spent decades building the model that gives 67. He is polite but unyielding. The Planck data are among the best characterized data sets in the history of science. Millions of hours of computer time have been spent testing for systematic errors. The 6 parameters of the lambda CDM model, including the Hubble constant, fit the data so well that adding more parameters makes the fit worse, not better. The model is minimal and accurate. It does not need modification. The conversation goes in circles. Every time Rees presents a new cross-check, a different distance indicator, a different sample of galaxies, a different analysis pipeline. Evstathiou nods politely and asks whether the same systematic errors might affect all of them. Every time Evstathiou presents the Planck consistency tests, Rees nods politely and points out that internal consistency does not prove external accuracy. A model can be internally consistent and still miss something about the real universe. Days pass. Whiteboards fill with equations. coffee is consumed in alarming quantities. And slowly, a kind of exhausted consensus emerges. Not a resolution, but a shared understanding of the shape of the problem. The consensus is this: both measurements are probably right, within their stated uncertainties given their assumptions. The error, if there is one, is not in the calibration of key-feed variables or the fitting of the Planck power spectrum. It is in the assumptions underlying the entire framework. Something is wrong, not with the data, but with the model. This is a strange conclusion to reach. It means the lambda CDM model, the standard cosmological model that has successfully described the universe for 2 decades, may be incomplete. Not in a minor way, in a fundamental way. In a way that affects the relationship between the early universe and the late universe, between what was happening when the cosmic microwave background was released and what is happening now, 13 billion years later. Stop and feel what that means. Lambda CDM is not a hypothesis. It is the consensus description of reality. It tells us the universe is 13.8 billion years old. It tells us ordinary matter makes up about 5% of the cosmic energy budget, dark matter about 27%, and dark energy about 68%. It tells us structure formed through gravitational collapse, seeded by tiny quantum fluctuations stretched to cosmic scales by inflation. It tells us the universe will expand forever, accelerating into an empty, cold future. This is the story we tell ourselves about the cosmos. This is the framework within which all other astrophysics operates, and the Hubble tension suggests it may be wrong. Not wrong in its broad outlines. The universe is still expanding. It is still old. It still contains dark matter and dark energy. But the details, the precise values of the parameters, the exact history of the expansion, the relationship between different epochs, may need revision. And revising a model this successful is not like fixing a typo. It is like discovering that the map you have been navigating by has a different scale in different regions. Let me show you what the theorists have tried. In the years since the tension became undeniable, dozens of proposals have emerged, new ingredients that could be added to the standard model to make it compatible with both measurements. Each proposal is a small act of imagination, a physicist asking, what if there is something we have not thought of? One proposal is called early dark energy. The idea is simple but radical. What if dark energy was not constant throughout cosmic history? What if there was a burst of dark energy-like behaviour very early in the universe, shortly before the cosmic microwave background was released? That then faded away. This burst would change the expansion rate at a critical moment, altering the sound horizon, the ruler we use to extract the Hubble constant from the CMB, and potentially reconciling the two measurements. The math is subtle, but instructive. Imagine the early universe as a hot, dense plasma. Sound waves, pressure waves, travel through this plasma at a well-defined speed, about 57% of the speed of light. The distance these waves travel before the plasma cools and becomes transparent is the sound horizon. The Planck satellite measures this distance by looking at the pattern of hot and cold spots in the microwave background. And here is the key. The Planck team does not measure the sound horizon directly. They measure its angular size, how big it appears on the sky. To convert that angle into a physical distance, and from that distance into a Hubble constant, they need to assume a particular expansion history. If the early expansion was faster than the standard model predicts, the sound horizon would be smaller, and the inferred Hubble constant would be higher. Early dark energy provides that faster expansion. By injecting additional energy into the universe shortly before recombination, it speeds up the cosmic clock, shrinks the sound horizon, and raises the Planck-derived Hubble constant toward the locally measured value. It sounds elegant. It sounds like a solution. But the universe is not so easily satisfied. The problem is that early dark energy does not only affect the sound horizon, it affects everything. It changes the timing of matter-radiation equality. It changes the growth of cosmic structure. It changes the abundance of light elements forged in the Big Bang. And when you fit an early dark energy model to all the data, not just the CMB, but the galaxy surveys and the supernova catalogues and the measurements of primordial helium, the fit gets worse, not better. The tension in one place creates tensions in other places. The solution to one problem becomes the source of new problems. This is the trap that theorists find themselves in. The lambda CDM model fits the data remarkably well. Any modification that solves the Hubble tension risks breaking something else. The model is tightly constrained, with very little room for new physics that does not leave fingerprints in other observations. Some physicists have proposed modifications to dark matter instead. What if dark matter is not perfectly cold and collisionless, as the standard model assumes? What if it has small interactions with itself, or with ordinary matter, or with some unknown particle? What if it decays into lighter particles over cosmic time? These proposals are collectively called interacting dark matter or decaying dark matter, and they too can shift the inferred Hubble constant. But they too create problems elsewhere, changing the clustering of matter in ways that conflict with observations of galaxy distributions or producing spectral distortions in the CMB that should be visible but are not. Other physicists have looked at the neutrino sector. Neutrinos are ghostly particles that barely interact with ordinary matter, but the universe is full of them, relics from the Big Bang, travelling at nearly the speed of light since the first second of cosmic history. The standard model assumes 3 species of neutrinos with very small masses, but what if there is a 4th species, a sterile neutrino that does not feel the weak nuclear force, invisible to all our detectors except through its gravitational effects? Such a particle would add to the cosmic energy budget in the early universe, speeding up the expansion and potentially resolving the tension. The math is suggestive. A single sterile neutrino with the right properties could raise the Planck-derived Hubble constant by 1 or 2 kilometers per second per megaparsec. But sterile neutrinos do not only affect the expansion rate, they affect the formation of structure, the clustering of galaxies, the growth of cosmic voids. And again, the constraints tighten. Again, the solution in one place becomes a problem in another. I am describing this in some detail because I want you to feel the texture of the problem. The Hubble tension is not a mystery that will be solved by a single clever idea. It is a web of interconnected constraints, a multidimensional optimization problem where every adjustment has consequences. The theorists are not failing because they lack imagination. They are failing because the data are too good. The measurements are so precise that there is very little room for new physics to hide. Let me give you a sense of the numbers. The CMB power spectrum, the pattern of hot and cold spots in the cosmic microwave background, contains thousands of data points. Each point is a measurement of how the temperature varies on a particular angular scale. The lambda CDM model fits these thousands of points with only 6 free parameters. The agreement is astonishing. Not rough agreement, but precise agreement, at the level of fractions of a percent. Every peak in the spectrum, every dip, every subtle oscillation is captured by the model. To appreciate how remarkable this is, consider what could go wrong. The physics of the early universe involves general relativity, quantum mechanics, nuclear physics, plasma physics, and the statistics of primordial fluctuations. Any error in any of these ingredients would show up as a mismatch in the CMB spectrum. But there is no mismatch. The model works. The same is true for the distance ladder. The Cepheid variable calibration involves stellar physics, dust absorption, metallicity effects, and the geometry of nearby galaxies. The Type Ia supernova measurements involve nuclear physics, binary star evolution, the composition of white dwarfs, and the light curve-fitting algorithms that convert brightness into distance. Any error in any of these ingredients would introduce scatter or bias in the Hubble constant. But the scatter is small, the consistency is high, and the final number, 73, has error bars of just 1%. Both methods are the products of decades of effort. Both methods have been cross-checked against independent techniques. Both methods claim to have identified and corrected their dominant systematic errors, and both methods cannot be right, not within the standard model. Let me put this differently. Imagine you're a detective investigating a locked room mystery. A man is found dead inside a sealed chamber with no windows and only one door, which was locked from the inside. 2 witnesses saw him enter. 2 witnesses saw him lock the door. The autopsy shows he was murdered. The physics of the situation says murder is impossible, and yet the body is there. The Hubble tension is a locked room mystery at cosmic scales. The early universe method measures one value. The late universe method measures another. Both methods are internally consistent. Both methods have been checked for systematic errors. Both methods claim to be measuring the same quantity, the current expansion rate of the universe, and the values disagree at 8 sigma. The physics of the situation says disagreement is impossible, and yet the disagreement is there. What do you do with a locked room mystery? Some detectives focus on the witnesses. Maybe someone is lying, maybe someone is mistaken, maybe the door was not actually locked, or the chamber was not actually sealed. This is the approach of those who hunt for systematic errors, scrutinizing the Cepheid calibration, questioning the dust models, testing the supernova light curve fitting. If the local measurement is wrong, the mystery evaporates. Other detectives focus on the body. Maybe the autopsy is flawed. Maybe the cause of death was misidentified. This is the approach of those who question the CMB analysis, asking whether the Planck power spectrum has been interpreted correctly, whether the model assumptions are biasing the results, whether a different cosmology would fit the data equally well. If the early universe inference is wrong, the mystery evaporates. But some detectives take a third approach. They accept that all the evidence is genuine. The witnesses are truthful, the chamber was sealed, the autopsy is accurate, and they look for an explanation that transcends the apparent constraints. A secret passage, perhaps. A poison that mimics natural causes. A conspiracy so subtle it escapes ordinary detection. This is the approach of those who believe the tension is real. They accept that both measurements are correct, within their stated uncertainties, and they look for new physics that would explain how the universe could yield two different values for the same constant. The most unsettling possibility is also the most exciting. Perhaps the Hubble constant is not actually constant. I mentioned this earlier, but let me dwell on it now, because it is the kind of idea that changes everything if true. The Hubble constant is defined as the current rate of expansion of the universe, the velocity at which distant galaxies are receding per unit distance. But the current rate of expansion is not a fixed quantity if the expansion rate is changing over time. In a universe with constant dark energy, the expansion rate in the future will be different from the expansion rate today, which is different from the expansion rate in the past. The Hubble constant is constant across space. At any given moment, every point in the universe sees the same expansion rate, but it varies across time. The standard model assumes that dark energy has a very specific form, a cosmological constant, a fixed energy density that does not change as the universe expands. This is the simplest possibility, mathematically. It corresponds to Einstein's original cosmological constant, the term he added to his equations and later called his greatest blunder. But it is not the only possibility. Dark energy could be dynamic. It could be a field that permeates space, evolving slowly as the universe ages. Such a field would have an equation of state, a parameter called W, that describes the relationship between its pressure and its density. For a cosmological constant, W equals exactly -1. For a dynamic field, W could be slightly greater or slightly less than -1, and it could change over time. If W is changing, the expansion history is richer than the standard model predicts. The universe might have expanded more slowly at some epochs, and more rapidly at others. The Hubble constant measured at different cosmic times would have different values, and the tension between the local measurement and the early universe measurement might be exactly what we would expect, not a sign of error, but a sign of discovery. This is called the dark energy evolution scenario, and it has been explored extensively in the theoretical literature. The simplest version involves a scalar field, a number at every point in space, like a temperature field, evolving according to some potential energy function. Such fields are natural in particle physics. They appear in models of inflation, in theories of supersymmetry, in attempts to unify the forces of nature. If one such field is responsible for dark energy, its evolution could leave imprints in the cosmic expansion history. The question is whether the data support this picture. Here the situation is subtle. The evidence for dark energy evolution is not conclusive. The standard cosmological constant, W equals -1 fixed forever, is still consistent with most observations, but there are hints, there are whispers in the data. The most significant hint comes from the Dark Energy Survey, a massive galaxy survey that has mapped hundreds of millions of galaxies across 8 years of observations. The survey measures the growth of cosmic structure over time, how galaxies clustered together, how voids expanded, how the cosmic web evolved from high-density fluctuations to the present-day pattern of filaments and walls. And the growth rate they measure is slightly slower than what the lambda CDM model predicts. Slightly slower. Let me be careful here. The discrepancy is small, a few percent. It is consistent with statistical fluctuations. It could be a systematic error in the data analysis, but it is there. and it points in the same direction as the Hubble tension, toward a universe that behaves differently than our models expect. If dark energy is evolving, if its density is increasing over time, or if its equation of state is shifting, then structure growth would indeed be suppressed. The extra acceleration from increasing dark energy would tear structures apart more effectively, preventing matter from clustering as tightly. The hints from galaxy surveys combined with the Hubble tension form a pattern. They are two independent lines of evidence pointing toward the same conclusion. But patterns can be coincidental, and hints can evaporate under scrutiny. In 2024, the Dark Energy Spectroscopic Instrument, DESO, released its first cosmological results. This was the most anticipated dataset in years. DESI is a robotic fiber-fed spectrograph mounted on a 4-meter telescope in Arizona, capable of measuring 5,000 galaxy spectra simultaneously. It is designed to map the three-dimensional distribution of galaxies with unprecedented precision, tracing the expansion history of the universe over the past 11 billion years. The first results were tantalizing. When the DESI team fit their data to a model with evolving dark energy, where it was allowed to change over time, the fit was better than the standard cosmological constant. Not dramatically better, not conclusively better, but measurably better. The data preferred a scenario where W started slightly greater than -1 at early times and decreased toward -1 more recently. This is exactly the pattern that could help resolve the Hubble tension. The cosmology community held its breath. But here is the thing about cosmology. One result is never enough. The history of the field is littered with anomalies that seemed significant at first and then faded away as more data accumulated. The Bicep 2 gravitational wave signal that turned out to be dust. The cosmic cold spot that might just be a statistical fluctuation. The early claims of WIMP detection that could not be replicated. Cosmologists have learned painfully to be patient. They have learned to wait for confirmation, and so the wait continues. DESI is still taking data. The Vera Rubin Observatory, currently under construction in Chile, will soon begin the largest galaxy survey ever attempted. 10 years of continuous observation, billions of galaxies, sensitivity to the faintest traces of dark energy evolution. The European Space Agency's Euclid mission, launched in 2023, is mapping the universe in the infrared, probing the growth of structure with new techniques. The Roman Space Telescope, NASA's flagship mission for the coming decade, will extend supernova measurements to higher redshifts than ever before. Within the next 5 to 10 years, the data will be good enough to distinguish between a cosmological constant and evolving dark energy. The hints will either harden into discovery or dissolve into noise. The Hubble tension will either be explained or will remain, sharpening into a deeper crisis. Let that sink in for a moment. We are living through a period when the basic description of the universe is genuinely uncertain, not uncertain in the philosophical sense. We always acknowledge the limits of knowledge, but uncertain in the practical sense. The measurements we're making now, the surveys we're conducting, the data we're collecting, these will decide the shape of cosmology for the next generation, and we do not yet know what they will say. This is what it feels like to be at the frontier. The textbooks describe cosmology as a science of precision measurements and elegant theories. They tell the story of discovery as if it were inevitable, a march from ignorance to knowledge, from confusion to clarity. But the reality is messier. The reality involves rooms full of tired scientists arguing about calibration techniques. It involves graduate students staring at error budgets at 2 a.m, wondering if they have missed something. It involves the uncomfortable awareness that the beautiful model on the whiteboard might not match the stubborn numbers on the screen. The Hubble tension is not a glitch to be fixed. It is a window into how science actually works. The slow accumulation of evidence, the tension between competing methods, the patience required to let the truth emerge from the noise, and yet patience is not passive. While the surveys accumulate their photons and the error bars narrow millimetre by millimetre, theorists are not sitting idle. They are building, they are speculating, they are constructing elaborate mathematical architectures designed to explain what might be happening if the Hubble tension turns out to be real, not a systematic error to be hunted and eliminated, but a genuine signal that the universe is stranger than the standard model admits. This is where the story takes a darker turn. Because if the tension is real, If the universe genuinely expands at different rates depending on how you measure it, then something fundamental must be wrong with our picture of cosmology. And the candidates for what might be wrong range from the merely surprising to the deeply unsettling. Let us start with the gentlest possibility. Perhaps dark energy is not constant. Perhaps the cosmological constant is not constant at all. We have already touched on this idea, but it deserves a slower examination because it is the most conservative exit from the crisis, the minimal departure from the standard model that could still explain the data. In Einstein's equations, the cosmological constant enters as a fixed number, lambda, a single value that remains unchanged throughout cosmic history. It pushes the expansion of the universe outward with the same relentless pressure whether you're looking at the cosmos 1 billion years ago, or 10 billion years ago, or today. The standard model assumes this because it is the simplest assumption, and simplicity has served physics well. But simplicity is not truth. It is a starting point. What if lambda is not a constant but a variable? What if dark energy has a value that slowly shifts over cosmic time, stronger in the past, weaker today, or vice versa? This would not require any dramatic new physics. It would just require admitting that the simplest assumption was too simple. Physicists have a name for this possibility. They call it quintessence. The name comes from the medieval concept of the fifth element, the ether that filled the heavens and made the celestial spheres rotate. The modern version is more prosaic. Quintessence is just a scalar field, a quantity that pervades all of space and evolves slowly over time. You can think of it as a kind of cosmic fluid whose pressure and density change as the universe ages. If dark energy is quintessence rather than a cosmological constant, then the expansion rate of the universe would not be the same at all epochs. And if the expansion rate changes, then the tension between early universe and late universe measurements might dissolve. The two methods would not be measuring the same thing after all. They would be measuring the universe at different moments in the evolution of dark energy, and finding different answers because the answers genuinely differ. This is what the DESI hints suggest. A dark energy that was slightly different in the past than it is today, not dramatically different. The changes are subtle, encoded in tiny shifts of the equation of state parameter W. But even subtle changes, accumulated over billions of years, could add up to a measurable discrepancy in the Hubble constant. The problem is that quintessence, for all its elegance, does not come for free. It requires new physics. Not exotic new physics, not physics that breaks the laws we know, but physics that adds to them. A new field, new parameters, new degrees of freedom that must be constrained by data. And so far, while the hints are tantalizing, they are not conclusive. The next generation of surveys will tell us whether quintessence is real or whether the cosmological constant survives after all, unchanged and unchanging, stubborn as ever. But let us push further. Let us consider what happens if quintessence is not enough. What if the tension cannot be resolved by tinkering with dark energy? What if something more fundamental is required? Here is where the theoretical landscape becomes strange. One possibility that has attracted serious attention is called early dark energy. This is different from quintessence, though the names sound similar. Early dark energy does not slowly evolve over all of cosmic history. Instead, it appears suddenly, plays a role at a specific moment in the universe's past, and then vanishes, like an actor who walks on stage for a single scene and then disappears into the wings, never to return. The specific moment is the era just before recombination. Remember that time, 400,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and the cosmic microwave background was released. The standard model says dark energy was negligible during this era. The universe was dense enough that matter and radiation dominated the expansion. Lambda was there, lurking, but it did not matter yet. Its influence would only become important billions of years later, after the matter had thinned out enough for dark energy's constant push to overwhelm matter's fading pull. But what if that picture is incomplete? What if there was a brief episode of dark energy, a temporary surge of accelerated expansion, just before recombination? This early dark energy would have changed the size of the sound horizon. Remember the sound horizon, that fundamental ruler encoded in the CMB. Its length depends on how fast the universe was expanding during the era when sound waves travelled through the primordial plasma. If early dark energy made the universe expand faster during that brief window, the sound horizon would be shorter than the standard model predicts. And if the sound horizon was shorter, then the Planck satellite, measuring that ruler without knowing it had been compressed, would infer a Hubble constant that was too low. This is a clever idea. It does not require changing physics in the late universe, where the distance ladder measurements live. It targets the early universe instead, adjusting the calibration that Planck uses. If the ruler was shorter, Planck's measurement of H0 would come up, potentially matching the distance ladder results. The problem is that early dark energy is not invisible. If it existed, it would leave fingerprints. The CMB is exquisitely sensitive to conditions in the early universe, and any new component, even a temporary one, would shift the pattern of temperature fluctuations in detectable ways. So far, the Planck data shows no clear evidence for early dark energy. The fits are not obviously better. The fingerprints have not been found. This does not rule out the idea entirely. The fingerprints might be subtler than current analyses can detect, or they might require new observations to reveal. But it does mean that early dark energy remains speculative, a possibility, not a solution. And there are other possibilities, each one stranger than the last. Consider modified gravity. The entire edifice of cosmology rests on Einstein's general theory of relativity. Every equation we write, every simulation we run, every measurement we interpret, all of it assumes that Einstein was right, that gravity works the way he said it works, that the geometry of space-time curves in response to mass and energy according to his field equations, and that those equations are correct on every scale from the solar system to the cosmic web. But what if Einstein was almost right? What if general relativity is an approximation, a spectacularly good approximation that works perfectly in the regimes we have tested, but that breaks down in subtle ways on cosmic scales or at cosmic ages? This is not as radical as it sounds. Einstein himself knew that his theory was incomplete. General relativity and quantum mechanics do not fit together. At the smallest scales and highest energies, the theory must be replaced by something else, a theory of quantum gravity that we do not yet possess. Most physicists assume that this breakdown only matters in extreme environments, black hole interiors, the first instance of the Big Bang, places where space-time curves so violently that classical concepts dissolve. But what if the breakdown also matters on the larger scales? What if there are corrections to general relativity that only become significant when you zoom out far enough? Corrections that leave the solar system unchanged but shift the expansion of the universe by a few percent. Physicists have proposed dozens of modified gravity theories over the years. Some add extra fields to Einstein's equations. Some change the mathematical structure of the equations themselves. Some propose that gravity weakens or strengthens in ways that depend on cosmic age. The names are technical and forgettable: FR, gravity, scalar tensor theories, massive gravity, Mond extensions to cosmology. But the underlying question is always the same. What if we've been measuring the expansion of a universe that does not obey the rules we think it obeys? The Hubble tension could be a clue that general relativity is fraying. The early universe measurements assume Einstein's equations when they model the CMB. The late universe measurements assume Einstein's equations when they interpret the redshifts of galaxies. If Einstein's equations are slightly wrong, if gravity is slightly different at different epochs or on different scales, then the two measurements might both be correct, but correct in the context of different underlying physics. They would not be measuring the same universe, because the universe itself would not behave the way we thought. This is a disturbing possibility. General relativity has been tested with extraordinary precision in the solar system, in binary pulsars, in the detection of gravitational waves. It passes every test we throw at it. To imagine that it fails cosmologically, that it is right at every scale we can directly probe but wrong at scales where we must infer, requires a kind of cosmic conspiracy. Why would gravity be so finely tuned to fool us at close range and betray itself only at the largest distances? And yet the history of physics is full of such betrayals. Newton's gravity worked perfectly for 3 centuries, passing every test from falling apples to orbiting moons to the paths of comets. And then Mercury's orbit showed a tiny anomaly, a precession of 43 arcseconds per century, and the entire theory collapsed. Einstein replaced Newton not because Newton was obviously wrong, but because Newton was almost perfectly right, except for one tiny discrepancy that pointed to deeper truth. Could the Hubble tension be our mercury? Could an 8 sigma disagreement in the expansion rate be the tiny crack that reveals the next revolution? It is too early to say. The modified gravity theories are not yet compelling. They often introduce new problems while solving old ones. They require fine-tuning of their own. They struggle to match the full range of cosmological observations as well as the standard model does, but they are being explored. And if the tension persists, if every systematic error is ruled out and every conventional explanation fails, then modified gravity will become a serious contender. The theorists who are building these frameworks now, mostly in obscurity, may one day be remembered as pioneers. Let us consider one more possibility, perhaps the strangest of all. What if the universe is not homogeneous? What if the fundamental assumption of modern cosmology, that the universe looks the same in every direction on large scales, is wrong? This assumption is called the cosmological principle. It is the bedrock on which all of cosmology is built. When we model the universe, we assume it has no center, no edge, no preferred direction. Every point in space is equivalent to every other point. Every direction is equivalent to every other direction. This is what allows us to write down a single number for the Hubble constant. If the universe were lumpy on large scales, if some regions expanded faster than others, if we happen to live in a local bubble with different properties than the average, then the Hubble constant would not be a constant at all. It would depend on where you looked and how far. The evidence for homogeneity comes from observations of the CMB and from surveys of the distribution of galaxies. On the larger scales we can measure, the universe does seem uniform. But uniform is a relative term. There are structures in the cosmos, voids, filaments, superclusters, that stretch for hundreds of millions of light years. Could there be even larger structures that we have not yet detected? Could we be living inside a vast underdensity, a bubble of space where matter is slightly thinner and expansion is slightly faster than the cosmic average? This is called the local void hypothesis, and it is remarkably difficult to rule out. If we lived in a local void, the distance ladder measurements, which are all made in our cosmic neighbourhood, would give systematically different results than the CMB measurements, which average over the entire observable universe. The apparent Hubble tension would not be a tension at all. It would just be the difference between local expansion and global expansion, a consequence of our location rather than our physics. The problem is that this hypothesis requires a very large void. To explain the full 8 sigma tension, the void would need to stretch for billions of light years. It would need to be the largest structure in the observable universe, and it would need to be centered on us, or at least contain us near its center, which raises uncomfortable questions about fine-tuning and anthropic reasoning. Why would we, of all observers, happen to live in such a special place? Moreover, a local void of this size should leave signatures in the CMB. We should see a cold spot in the direction of the void, a shadow cast by our peculiar location. We should see asymmetries in the distribution of galaxies that reveal the void's edges. So far, these signatures have not been found. The void hypothesis remains alive, but on life support, invoked mostly when all other options seem exhausted, and perhaps that is the point. Perhaps the real lesson of the Hubble tension is that we are running out of conventional explanations. The systematic errors have been chased. The local voids have been searched. The modified theories have been constrained. And still the tension persists. What remains is either a mistake we have not yet found, somewhere in the long chain from Cepheid light curves to cosmological parameters, a subtle error is hiding, or new physics that we cannot yet describe. This uncertainty is uncomfortable. Physicists prefer clean answers. They prefer theories that make predictions and data that confirms or refutes them. The Hubble tension offers neither. It sits in the gap between certainty and confusion, a question that cannot yet be answered. But perhaps this is what progress looks like. Perhaps the most important discoveries do not announce themselves with trumpets. They begin with a quiet disagreement, a number that does not match, a discrepancy that refuses to go away. The scientists who first noticed that the universe was accelerating did not set out to discover dark energy. They were trying to measure how fast the universe was slowing down. The anomaly was unwanted, uncomfortable, impossible to explain. And then it turned out to be the most important result in cosmology in decades. The Hubble tension may be the same kind of anomaly. We do not yet know what it means, but we know that it is real enough to take seriously. real enough to launch satellite missions, real enough to build new telescopes, real enough to keep thousands of scientists awake at night, staring at error budgets and calibration curves and the stubborn gap between two numbers that should agree but do not. There is a strange beauty in this. The universe is teaching us something, and we are still learning to listen. The measurements are speaking, and we are still learning to interpret what they say. Think about what that means for a moment. We have built instruments capable of measuring the expansion of the cosmos to within 1 or 2% precision. We have developed independent methods that agree with each other to within that margin, and yet they disagree with each other by more than 5 standard deviations. This is not a failure of science. This is science working exactly as it should, exposing the edges of our knowledge, revealing the places where our understanding breaks down. The next decade will be decisive. The surveys are running. The photons are being collected. Somewhere in the data that is being gathered right now, in the spectra of distant galaxies, in the light curves of supernovae, in the subtle lensing patterns of the cosmic web, there may be the answer to a question we have been asking for nearly a century. How fast is the universe expanding? And why can we not agree on the answer? The tension remains, the debate continues, and somewhere in the gap between 67 and 73 kilometers per second per megaparsec, the future of cosmology is waiting to be discovered. But this is not merely an academic debate conducted in conference rooms and journal pages. The Hubble tension reaches beyond the technical disagreement about calibration and systematics. It touches something deeper, a question about the nature of scientific knowledge itself, about what it means to measure something that cannot be directly observed, about the faith we place in our instruments and our models and our long chains of inference. Because here is what is easy to forget when you read about precision cosmology. We cannot see the Hubble constant. We cannot point to it, cannot photograph it, cannot touch it. The Hubble constant is an abstraction, a parameter in a mathematical model that we believe corresponds to something real. We measure redshifts and distances and luminosities. We feed these measurements into equations, and out pops a number that we call h0. But between the photons and the parameter lies an entire edifice of assumptions, each one tested as rigorously as we can manage, but each one ultimately an act of interpretation. This is why the tension is so disturbing. It is not just a disagreement about numbers, it is a disagreement about interpretation. The distance ladder team and the Planck team are looking at different photons, making different measurements, using different methods, and they are both confident in their results. Both teams have checked their work. Both teams have hunted for systematic errors. Both teams believe they are measuring the true Hubble constant, and they cannot both be right. Unless, of course, the concept itself is the problem. Unless the Hubble constant is not constant at all, not a single number describing a uniform expansion, but a local approximation that depends on where and when you measure. This would be a revolution in our understanding, not just of cosmology, but of what it means to measure the universe at all. The standard model assumes that space is homogeneous and isotropic. This is not an empirical fact, it is a philosophical starting point. We adopt it because it is the simplest assumption, because it makes the mathematics tractable, because the observations are consistent with it to the precision we can achieve. But what if our precision has now exceeded the truth of the assumption? What if we have measured well enough to see the breakdown of homogeneity, and we are interpreting the breakdown as a tension? This is speculative. There is no compelling evidence for large-scale inhomogeneity in the universe. But the fact that we are asking the question at all, the fact that serious cosmologists are publishing papers on local voids and anisotropic expansion, tells you something about the state of the field. The tension has opened a door that was previously closed. Ideas that would have been dismissed a decade ago are now being taken seriously, not because the evidence supports them, but because the evidence demands alternatives. And so we wait. We wait for DESI to finish its survey and release its final results. We wait for Euclid to map the dark side of the universe. We wait for Rubin to photograph billions of galaxies. We wait for Roman to extend the supernova distance ladder to redshifts beyond 1, where dark energy's influence is stronger and more detectable. We wait for the theorists to propose new models and for the observers to test them. We wait with the patience that cosmology has always demanded, the patience of scientists who measure light that has travelled for billions of years, who infer the properties of the universe from whispers and shadows, who know that the answers they seek may not come in their lifetimes. This is the reality of working at the frontier. The textbooks tell a clean story because they are written after the fact, after the tension has been resolved and the new physics has been incorporated and the names of the discoverers have been recorded. But the scientists doing the work live in the messy middle, the uncertain present, the period when the answer is genuinely unknown. The Hubble tension is not a problem to be solved and forgotten. It is a symptom of something deeper, a sign that our model of the universe, for all its successes, may be incomplete. And that incompleteness is not a failure. It is an invitation. It is the universe saying, look closer, measure better, think harder. There is something here you have not understood. Let me now tell you about the hardest implication of all, the one that cosmologists discuss in conference hallways and late-night email threads, but rarely say plainly in public. It is the implication that emerges when you take the tension seriously, when you stop treating it as a problem to be solved and start treating it as a message to be received. Because here is the uncomfortable truth that hangs over every proposed solution, every new measurement, every theoretical tweak. If the tension is real, if it persists despite every systematic check and every calibration improvement and every independent verification, then we have been wrong about something fundamental. Not wrong in a small, correctable way, wrong in a way that requires us to rebuild the foundation. And the foundation we're talking about is not some obscure corner of physics. It is our entire understanding of how the universe works. Consider what lambda CDM actually claims. It claims that the universe is filled with three components: ordinary matter, cold dark matter, and dark energy in the form of a cosmological constant. It claims that these components have specific properties. Ordinary matter clumps and gravitates. Dark matter clumps and gravitates but does not interact with light. Dark energy has constant density and pushes space apart at an accelerating rate. It claims that the initial conditions of the universe were set by inflation, a brief period of exponential expansion that stretched quantum fluctuations into the seeds of cosmic structure. It claims that gravity works according to general relativity on all scales, from the solar system to the observable universe. It claims that the laws of physics are the same everywhere and everywhen, that a hydrogen atom in a distant galaxy emits the same spectral lines as a hydrogen atom in a laboratory on Earth, that the gravitational constant has the same value in the first second after the Big Bang as it does today. These are not minor assumptions. They are the load-bearing walls of the entire edifice, and the Hubble tension, if it is real, suggests that at least one of them is wrong. Let me walk you through the possibilities, one by one, and let you feel the weight of each. The first possibility is that dark energy is not constant. This is perhaps the least disturbing option, which is why many cosmologists hope it is true. In this scenario, the cosmological constant, the lambda in lambda CDM, is not actually constant at all. It is a dynamical field that changes over time, growing stronger or weaker as the universe evolves. If dark energy was weaker in the past and stronger today, then the universe would have expanded more slowly in its early history and more quickly in its recent history. The CMB would record the slower early expansion, giving a lower value of h0. The distance ladder would measure the faster recent expansion, giving a higher value. The tension would be explained not by an error in either measurement, but by a genuine change in the properties of space itself. This sounds almost reassuring until you think about what it means. If dark energy is dynamical, then we have no idea what it is. The cosmological constant, for all its problems, has a certain elegance. It is just a property of empty space, a constant energy density that gravity interprets as repulsive pressure. But a dynamical dark energy requires a physical mechanism. Something has to be changing. There has to be a field, a substance, a process that drives the variation. And we have no idea what that field is, no idea what governs its behavior, no idea why it would change in just the way required to explain the tension. We would be trading one mystery for a deeper one. The DESI results I mentioned earlier hint at exactly this possibility. The baryon acoustic oscillation data suggests that the equation of state parameter, the number that describes how dark energy responds to expansion, may be evolving with time. If confirmed, this would be extraordinary. It would mean that dark energy is not a cosmological constant, but something else entirely, something that changes, something that has its own dynamics and its own history. The universe would not be accelerating at a constant rate, but at a rate that itself accelerates or decelerates, depending on cosmic epoch. The fate of the cosmos, whether it expands forever, whether it eventually tears itself apart, whether it somehow reverses and contracts, would depend on the future behaviour of a field we do not understand and cannot predict. Stop and feel the weight of that for a moment. We thought we knew how the universe would end. The cosmological constant implied a cold, dark, ever-expanding future. Galaxies receding forever, stars burning out, space stretching toward infinite emptiness. This was not a cheerful picture, but it was at least a stable one. We had reached the end of cosmic history in outline form, but if dark energy is dynamical, then we do not know the ending. The future is genuinely unknown. The universe might accelerate forever, or it might coast, or it might reverse, or it might do something we have not yet imagined. Our predictions about the far future are not pessimistic certainties, but provisional guesses, subject to revision as we learn more about a phenomenon we barely understand. The second possibility is that the early universe contains something we have not accounted for. This is the domain of early dark energy, extra radiation, additional neutrino species, and other exotic proposals. The idea is that the universe, in its first few 100,000 years, had a different composition than we currently assume. Perhaps there was an additional component, a field that contributed to the energy density, altered the expansion rate, and then decayed or diluted away before the present day. This component would have left its mark on the CMB, subtly shifting the acoustic peaks in ways that our current models do not capture. If we accounted for it properly, we would infer a higher H0 from the Planck data, and the tension would disappear. This sounds plausible in principle. The early universe was hot, dense, and filled with phenomena we cannot directly observe. It is not absurd to imagine that something was present then that is absent now. But when you examine the proposals in detail, they all face the same problem. The CMB is remarkably well fit by the standard model. There is very little room for additional components. The Planck data are precise enough to constrain the early universe's composition to a few percent, and every proposed addition has to thread a needle. It has to be significant enough to explain the tension, but subtle enough to avoid disrupting the fit to the observed power spectrum. This is not a criticism of the proposals, it is a description of the predicament. The very precision that makes the CMB such a powerful tool also makes it a harsh judge. Any modification to the early universe has to survive scrutiny against hundreds of data points measured to fractions of a percent. Most modifications fail. The ones that survive are finely tuned, requiring specific properties and specific decay rates, and specific interactions that feel more like engineering than physics. We are not discovering a natural explanation, we are constructing one to fit the data, and while this is not disqualifying, all models are constructed, it is a warning sign. A solution that requires extensive tuning is often a sign that we have not found the true underlying cause. The third possibility is that our understanding of gravity is incomplete. This is the most radical option, and for that reason many cosmologists resist it. General relativity has been tested to extraordinary precision in the solar system, in binary pulsars, in gravitational wave observations. It predicted the existence of black holes and gravitational lensing, and the behaviour of space-time around massive objects. It has never been wrong within its domain of applicability. But here is the question. What is that domain? General relativity was developed and tested primarily in strong-field environments, places where gravity is intense and space-time is sharply curved. The solar system is such an environment on cosmic scales, though it feels mundane to us. Binary pulsars are definitely such environments. Black holes are the ultimate strong-field tests. But cosmology operates in a different regime entirely. On cosmological scales, gravity is weak but cumulative. The curvature of space-time is gentle but extends across billions of light-years. We are not measuring the orbit of a planet around a star. We are measuring the expansion of space itself, the large-scale structure of matter, the evolution of cosmic acceleration. It is at least conceivable that general relativity, while perfectly accurate in the strong-field regime, is subtly wrong in the cosmological regime. Modified gravity theories, FR gravity, scalar tensor theories, massive gravity, and dozens of others explore this possibility. They typically agree with general relativity in all the places where general relativity has been tested, and diverge only on cosmic scales. If one of these theories is correct, then our interpretation of both the CMB and the distance ladder would need to be revised. The tension might not be about the expansion rate at all, but about a mismatch between the true gravitational theory and the theory we've been using to analyse our data. This possibility is deeply uncomfortable because general relativity is not just a successful theory, it is a beautiful one. Einstein's equations have an elegance that physicists describe in almost aesthetic terms. They follow necessarily from a small number of principles, the equivalence of gravity and acceleration, the curvature of space-time, the conservation of energy momentum. To modify them is to break that elegance, to add terms and parameters that do not emerge from first principles, but are bolted on to fit the data. Most physicists resist this instinctively. They would rather discover new particles than new gravity. But instinct is not evidence. The universe is under no obligation to be elegant by human standards. If the Hubble tension is telling us that general relativity fails on cosmic scales, then our aesthetic preferences are irrelevant. The universe is what it is. The fourth possibility is the most troubling of all. It is the possibility that we have been wrong about the structure of spacetime itself, that the assumption of homogeneity and isotropy, the cosmological principle that underlies all of modern cosmology, is not quite true. Let me explain what this would mean. When we say the universe is homogeneous and isotropic, we mean that it looks roughly the same from any location and in any direction. There is no centre, no edge, no preferred position. The cosmic microwave background confirms this to extraordinary precision. The temperature is the same in all directions to 1 part in 100,000, with tiny fluctuations that represent the seeds of structure formation. This uniformity is the justification for treating the universe as a single system that can be described by a single expansion rate. But what if the uniformity is approximate? What if, on scales we have not fully mapped, the universe is slightly inhomogeneous, denser in some regions, sparser in others, expanding at different rates in different places? This would not violate any observations we have made so far, because all our observations are made from a single vantage point. We see the universe from Earth, from our galaxy, from our local group. If there are large-scale variations in density or expansion that manifest only on scales larger than our observational horizon, we would not detect them directly. We would only see their effects, subtle distortions in our measurements, apparent tensions that cannot be explained by a uniform model. This is speculative. I want to be clear about that. There is no compelling evidence for large-scale inhomogeneity, no smoking gun that says the cosmological principle is wrong. But the Hubble tension has forced cosmologists to consider possibilities they would never have entertained a decade ago. Papers are being published on local voids, on anisotropic expansion, on the possibility that our location in the universe is not quite average. These papers are not claiming to have solved the tension. They are claiming that the tension is severe enough to warrant exploring even the most foundational assumptions. And here is what makes this possibility so troubling. If the cosmological principle is wrong, then we do not have a single Hubble constant. The expansion rate would depend on where you measure it and in which direction. The entire framework of a universal H0 would be a local approximation, valid in our neighbourhood but not necessarily valid elsewhere. We would not be measuring the expansion of the universe. We would be measuring the expansion of our patch of the universe, and other patches might be different. Think about what this would mean for our understanding of cosmic history. The Big Bang, cosmic inflation, nucleosynthesis, recombination, structure formation. All of these depend on the assumption that the universe evolves as a single system with uniform properties. If that assumption fails, then our story of the cosmos becomes local, contingent, incomplete. We would know the history of our bubble, our island, our neighbourhood. But we would not know whether that history applies to regions we can never observe. This is the edge of the known. This is where the Hubble tension leads if you follow it to its logical conclusion. Not to a tidy solution, a new particle, a revised calibration, a subtle systematic error, but to a fundamental uncertainty about the nature of space and time and our ability to comprehend a universe that may be stranger than any single framework can describe. I do not want to leave you with the impression that cosmology is in crisis, that the field is collapsing, that nothing we have learned can be trusted. That would be wrong. Lambda CDM remains the most successful model of the universe ever constructed. Its predictions have been confirmed across scales ranging from the millimetre to the megaparsec. The evidence for dark matter and dark energy is overwhelming. accumulated over decades of independent observations. The cosmic microwave background is understood in exquisite detail. The formation of galaxies and galaxy clusters is explained by simulations that reproduce the observed universe with remarkable fidelity. The Hubble tension is a crack in this edifice, but a crack is not a collapse. It is a sign of stress, a warning that something needs attention, a place where new physics might emerge. The history of physics is filled with such cracks, small discrepancies that seemed like annoyances but turned out to be doors to new understanding. The precession of Mercury's orbit was a crack in Newtonian gravity. The ultraviolet catastrophe was a crack in classical thermodynamics. The muon magnetic moment anomaly, which persists to this day, may be a crack in the standard model of particle physics. Not every crack leads to revolution. Some are resolved by better measurements or subtler errors than anyone expected. But the pattern is clear. When two well-tested methods disagree, the disagreement is worth taking seriously. Something is happening. Something is being revealed. And this is where the Hubble tension stands today. Not resolved, not dismissed. Persistent, growing, 8 sigma and climbing. The measurements get better every year, the telescopes get sharper, the surveys get deeper, the systematic errors get smaller, and the tension does not go away. It sits there, calm and insistent, waiting to be understood. There is a phrase cosmologists use when they do not know the answer. They say, "We are statistics limited." It means that the uncertainty in their measurement is dominated by random noise, by the finite number of objects observed, by the need for more data. This is the happy situation, the one where patience and telescope time will solve the problem. But there is another phrase, rarer and more troubling. They say, "We are systematics limited." It means that the uncertainty is dominated by things they do not understand, biases in their instruments, assumptions in their models, effects they have not accounted for. This is the worrying situation because more data may not help. More data might just confirm the bias. The Hubble tension has pushed cosmology into a third category, one without a standard name. We might call it understanding limited. The measurements are good. The systematics have been hunted. The models have been tested. And the disagreement remains. The limiting factor is not noise or bias, but comprehension. We do not understand what the universe is telling us. This is humbling. It is also, if you let yourself feel it, exhilarating. Because understanding limited problems are the most valuable kind. They are the places where science advances not through incremental improvement, but through conceptual breakthrough. They are the problems that win Nobel Prizes, not for the people who measure more precisely, but for the people who finally understand what the measurements mean. Someone, somewhere, working today or in the decades to come, will solve the Hubble tension. They will find the key, the missing component, the flawed assumption, the new physics hiding in plain sight, and when they do, our picture, and that invitation has a texture to it, a specific quality that separates it from every other open question in physics. Because the Hubble tension is not like dark matter, where the mystery is what something is. It is not like quantum gravity, where the mystery is how to reconcile two frameworks. The Hubble tension is more intimate than that. It is the universe telling us that the single simplest thing we thought we could measure, the rate at which everything is moving away from everything else, may not mean what we thought it meant. And to understand why that is so deeply unsettling, you have to understand what the Hubble constant was supposed to be. It was supposed to be the anchor. In a universe full of dark unknowns, full of invisible matter and invisible energy and invisible fields, the Hubble constant was the one number that connected the theoretical model to the real, observed, photographable sky. You measure how fast galaxies are receding. You measure how far away they are. You divide one by the other, and you get a number. That number tells you the current expansion rate, and from that rate you can work backward through time, through the equations of general relativity, through the thermal history of the cosmos, all the way back to the first fraction of a second after the Big Bang. The Hubble constant is the hinge. It connects the universe you can see to the universe you can calculate. And if the hinge is broken, if the number depends on which direction you approach it from, then the door does not close properly. The model does not fit. This is not abstract. Let me show you what breaks. If the Hubble constant is 73, as the distance ladder suggests, then the universe is younger than if it is 67. the difference is not trivial. At 73, the age of the universe comes out to roughly 12.8 billion years. At 67.4, it comes out to 13.8 billion years. That is a gap of 1 billion years. 1 billion years during which stars could form and die, galaxies could merge and restructure, heavy elements could accumulate in the cores of aging suns and be scattered by supernova into the raw material for rocky planets and liquid water and the slow, patient chemistry of life. 1 billion years is not a rounding error. It is a geological epoch multiplied by 1,000, and the age is just the beginning. If H0 is higher, then the universe has been expanding faster, which means it reached its current size sooner, which means the distances we calculate to distant objects shift, which means the amount of dark energy required to produce the observed acceleration changes, which means the density of matter at early times changes, which means the predicted pattern of the cosmic microwave background shifts in subtle but detectable ways. Everything is coupled. Pull one thread, and the entire tapestry moves. The Hubble constant is not an isolated number. It is woven into every other parameter in the standard cosmological model. The matter density, the dark energy density, the curvature of space, the amplitude of primordial fluctuations, the spectral index that describes how those fluctuations vary with scale. Change H0 by 6 kilometers per second per megaparsec, and you have to change all of them. And when you change all of them, the model that previously fit the data beautifully begins to strain at its seams. This is what keeps cosmologists awake. Not the disagreement itself, but the cascade. The fear that resolving the tension will require not a small adjustment, but a fundamental restructuring. Let me put that fear into concrete terms. There is a quantity in cosmology called S8. It measures how clumpy the universe is, how much matter has gathered into clusters and filaments, versus how much remains smoothly distributed. The Planck satellite predicts a specific value for S8 based on its measurements of the cosmic microwave background and the standard model. And when observers go out and count galaxy clusters directly, weigh them using gravitational lensing, map the large-scale distribution of matter using surveys like the kilo-degree survey or the dark energy survey, they get a value that is slightly lower. The universe appears to be less clumpy than the standard model predicts. The significance of this discrepancy has hovered around 2 to 3 sigma for years, not dramatic enough to declare a crisis, but persistent enough to cause discomfort. And here is the part that makes you uneasy. The S8 tension and the H0 tension point in the same direction. Both suggest that the standard model's predictions, when projected forward from the early universe, slightly overshoot what we actually observe in the late universe. The early universe model predicts a cosmos that is expanding a little more slowly and clumping a little more aggressively than what the late universe measurements reveal. That is a pattern. That is not two independent flukes. That is two different measurements of two different quantities using two different techniques, both whispering the same thing. Something about the late universe does not match what the early universe promised. Stop and feel the weight of that for a moment. The cosmic microwave background is a snapshot of the universe at an age of 380,000 years. The distance ladder and the galaxy cluster surveys are measurements of the universe at an age of nearly 14 billion years. The standard model is the bridge between them, the mathematical machine that takes the early snapshot as input and predicts what the late universe should look like. And the prediction is slightly persistently uncomfortably wrong, not in a random direction, in a specific direction. The late universe is expanding faster and clumping less than the early universe said it should. If this were a single measurement, you could dismiss it. If it were a single technique, you could suspect a systematic error, but it is not. It is a convergence of independent lines of evidence, each one imperfect on its own, each one suggestive only in the context of the others, but together forming a pattern that the standard model does not naturally produce. Now. There are sober voices in this debate, and they deserve to be heard. Not every cosmologist agrees that the pattern is real. Some argue that the S8 tension is weaker than it appears, that different analysis choices can bring the cluster counting measurements into better agreement with Planck. Some point out that the systematic uncertainties in weak gravitational lensing surveys are still being understood, that the shear calibration and the photometric redshift estimates introduce biases that could shift the results. These are valid concerns. The S8 discrepancy has not reached the statistical threshold of the Hubble tension. It is a suggestion, not a proof, but even the skeptics acknowledge that the coincidence is uncomfortable. Two tensions, same direction, same implication. That is the kind of coincidence that either means nothing or means everything, and you cannot tell which until the data improve, and the data are improving. This is the part of the story where the instruments take centre stage, not because they are glamorous, but because they are the only honest arbiters we have. Consider the dark energy spectroscopic instrument DZ, mounted on the Mail telescope at the Kitt Peak National Observatory in Arizona, a 4-metre mirror staring upward through the desert night. DESI is not a camera. It is a robotic fibre optic system. 5,000 tiny glass fibres, each one thinner than a human hair, each one independently positioned by a small robotic arm to point at a different galaxy in the telescope's field of view. In a single exposure, DESI captures the spectra of 5,000 galaxies simultaneously. Each spectrum reveals a redshift. Each redshift reveals a distance and a recession velocity. Over its 5-year survey, DESI will measure the spectra of roughly 40 million galaxies and quasars, producing the most detailed 3-dimensional map of the universe ever constructed. What DESI measures specifically is something called the baryon acoustic oscillation signal, the same relic sound wave imprinted on the cosmic microwave background, but now measured not in microwave photons but in the distribution of galaxies across the sky. The sound wave left its mark everywhere. In the early universe, it shows up as temperature ripples in the background radiation. In the late universe, it shows up as a slight preference for galaxies to be separated by a characteristic distance, about 500 million light-years in today's stretched-out cosmos. That characteristic distance is a standard ruler. If you know how long the ruler is in physical terms, and you do, because the physics of the early universe tells you, and you measure how large it appears at different redshifts, you can determine how the expansion rate has changed over time. Not just what H0 is now, but what it was at redshift 0.5, at redshift 1, at redshift 2, at redshift 3. This is the critical capability. The distance ladder tells you H0 today. The cosmic microwave background tells you what H0 should be today, based on the early universe. DESI tells you the history in between. It fills in the gap. It shows you whether the expansion rate evolved smoothly, as the standard model predicts, or whether something unexpected happened along the way, a transition, a shift, a slow drift in the properties of dark energy that would cause the early universe prediction and the late universe measurement to diverge. And in April of 2024, DESI released its first-year results. 40 million spectra were not yet available. The release covered the first year of data, a fraction of the full survey. But even that fraction contained hints. The baryon acoustic oscillation measurements, when combined with supernova data and cosmic microwave background data, showed a mild preference. Not a strong detection, not a definitive result, but a mild preference for dark energy whose equation of state changes with time. The parameter W, which describes the ratio of dark energy's pressure to its density, and which the standard model fixes at exactly -1, appeared to drift. At early times it sat slightly below -1. At later times it appeared to be crossing toward values above -1. The significance was modest. 2 to 3 sigma, depending on the analysis choices. But there it was again, the same whisper. Something in the late universe is not quite what the standard model promised. Let me be careful here, because this is where the story becomes seductive and seduction is the enemy of accuracy. A 2 sigma hint in a first-year data release is not a discovery. It is a suggestion. It is the kind of signal that has appeared before in cosmological data and later faded as the statistics improved and the systematic errors were better understood. The history of cosmology is littered with 2 sigma hints that turned out to be noise, phantom detections of gravitational waves in the microwave background, apparent anomalies in the cosmic microwave background that dissolved under closer scrutiny, dark energy measurements that seemed to favour exotic models, and then regressed to the cosmological constant as the data matured. Every working cosmologist knows this history. Every working cosmologist has been burned by preliminary results that looked thrilling and turned out to be dust. And yet, the DESI hint does not exist in isolation. It arrives into a field already primed by the Hubble tension already suspicious that the cosmological constant may be too simple, already accumulating small discrepancies that individually mean little but collectively form a pattern. Context matters. A 2 sigma hint in a vacuum is barely worth mentioning. A 2 sigma hint that aligns with an 8 sigma tension, and a 2 to 3 sigma clustering discrepancy, and a growing theoretical discomfort with the unnaturalness of the cosmological constant. That is something different. That is not a detection. It is a direction. It is a compass needle that may be trembling toward north, and DESI is only the beginning of its survey. 3 more years of data remain to be collected and analysed. Each year the statistical power doubles, then triples, as the volume of sky surveyed grows and the number of galaxy spectra accumulates. If the hint persists, if the preference for evolving dark energy strengthens as the data deepen, then by 2027 or 2028 the significance could cross the threshold from suggestive to compelling. And if it crosses that threshold, the standard model of cosmology will require revision. Not a patch, not an additional parameter tucked into a corner, a new understanding of what dark energy is and how it behaves. But DESI is not alone in the dark. The Euclid Space Telescope, launched by the European Space Agency in July of 2023, orbits the second Lagrange point, the same gravitational perch that hosts the James Webb Space Telescope, 1.5 million kilometers from Earth, a quiet place where the sun and the Earth and the moon are all behind you, and the deep sky opens up in every direction. Euclid carries 2 instruments, a visible light camera and a near-infrared spectrometer and photometer. Over its 6-year mission, it will survey 15,000 square degrees of sky, more than a third of the entire celestial sphere, and catalogue billions of galaxies out to redshifts of about 2, when the universe was roughly 3.3 billion years old. Its primary targets are the same 2 phenomena that DESI measures from the ground: baryon, acoustic oscillations, and weak gravitational lensing. But Euclid measures them from space, above the atmosphere, with a stability and a uniformity of calibration that ground-based surveys cannot match. The atmosphere distorts images, it introduces noise, it varies from night to night, from minute to minute. Space does not. Euclid's measurements of galaxy shapes, the tiny distortions caused by gravitational lensing, distortions at the level of a fraction of a percent of a galaxy's apparent ellipticity, will be the cleanest ever obtained. And from those shapes, Euclid will reconstruct the distribution of all matter, dark and luminous, across the sky and across cosmic time. It will measure S8 with unprecedented precision. It will measure the growth rate of structure. It will test whether the universe clumps as the standard model predicts, or whether the slight deficit observed by previous surveys is real. Imagine the data these instruments are gathering even now as you listen to this. Photons that left their source galaxies billions of years ago, travelling across the expanding void, passing through the gravitational fields of intervening matter, arriving at last at the focal plane of a mirror, and being recorded, digitized, stored, transmitted back to Earth, analysed by algorithms and checked by human eyes. Each photon a messenger, each spectrum a sentence in a language we are still learning to read. The universe is not withholding the answer. It is broadcasting it in every direction, at every wavelength, at every moment. The question is whether our instruments are sensitive enough and our models flexible enough to hear what is being said. And then there is the Vera C. Rubin Observatory, still under construction on the summit of Cerro Pachon in the Chilean Andes, at an altitude of 2,500 meters, where the air is thin and the sky is dark and the Milky Way arches overhead, with a clarity that lowland observers never see. Rubin is not a space telescope. It is a ground-based survey machine, the widest, deepest, most rapid sky survey ever attempted. Its primary mirror spans 8.4 meters. Its camera is the largest ever built for astronomy, a 3.2 gigapixel detector that weighs nearly 3 metric tons. When it begins full operations, Rubin will photograph the entire visible southern sky every 3 nights, accumulating a movie of the changing universe that will run for 10 years. Over that decade, it will detect and catalogue approximately 20 billion galaxies and roughly 17 billion stars. Let that number breathe. 20 billion galaxies, each one a gravitational island of hundreds of billions of stars, each one a data point. For the Hubble tension, Rubin's contribution will be specific and powerful. It will discover hundreds of thousands of Type Ia supernovae, the standardizable candles that form the upper rungs of the distance ladder, not dozens as Rees's original 1998 discovery used, not hundreds as current surveys provide, hundreds of thousands, spanning a wide range of redshifts, observed with consistent photometry over a long baseline. This statistical power will do something that previous supernova surveys could not. It will allow cosmologists to test whether the supernova distance-luminosity relation is truly universal, or whether it shifts subtly with redshift, with host galaxy properties, with environment. If there is a hidden systematic error in the supernova calibration, some unrecognized dependence on metallicity or progenitor mass or dust properties, Rubin's enormous sample will reveal it. And if there is no such error, if the supernovae really are as standard as we believe, then Rubin's measurements of the expansion history will be the most precise ever obtained, and they will either confirm or refute the DESI hint of evolving dark energy with statistical authority that no previous experiment could muster. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA no earlier than 2027, will push even further. Roman carries a detector array the size of a large dinner table, a 2.4-metre mirror with a field of view 100 times wider than the James Webb Space Telescope's primary camera. It will conduct a supernova survey designed explicitly to measure dark energy, observing Type Ia supernovae at redshifts beyond 1, deep into the epoch when dark energy was just beginning to dominate the expansion, when its influence was growing, but had not yet overwhelmed the gravitational pull of matter. These high redshift supernovae are the most valuable for testing dark energy models, because they sample the transition era, the period when the universe shifted from decelerating to accelerating. Measuring the expansion rate across that transition with high precision will constrain the equation of state of dark energy in a regime that previous surveys could not reach. So the instruments are converging, ground and space, optical and infrared, spectroscopy and photometry, baryon acoustic oscillations and gravitational lensing and supernova distances and galaxy clustering. Each technique has its own systematics, its own blind spots, its own failure modes, but they are independent. They do not share calibrations. They do not share atmospheric effects. They do not share detector biases. If they all agree, if DC and Euclid and Rubin and Roman all point to the same conclusion, then the conclusion will be robust in a way that no single experiment could achieve. And if they disagree, if different techniques point in different directions, that disagreement will itself be informative, revealing which systematic errors matter and which assumptions are failing. This is how science works at the frontier. Not with a single decisive experiment, but with a slow convergence of independent lines of evidence, each one uncertain on its own, each one valuable only in the context of the others. The answer to the Hubble tension will not arrive as a headline. It will arrive as a gradual tightening of constraints, a slow narrowing of possibilities, a quiet accumulation of data points that eventually make one interpretation untenable and another unavoidable. It will arrive the way the evidence for dark energy itself arrived, not as a flash of insight, but as a growing weight of observation that the community could no longer ignore. And the theorists are not idle while they wait. In offices and on blackboards and in the quiet hours of computational runs, they are building alternatives, not speculations, calculations, models with specific predictions that can be tested against the incoming data. If dark energy evolves, what specific signature should DZ see in its baryon acoustic oscillation measurements? If early dark energy existed, what specific imprint should it leave on the cosmic microwave background at small angular scales? If the universe is slightly inhomogeneous on large scales, what specific pattern should appear in the distribution of galaxy clusters? Each alternative model makes quantitative predictions, and each prediction can be compared against the data when the data arrive. The theorists are laying traps. The observers are building instruments to spring them. There is something quietly magnificent about this process if you let yourself see it. Thousands of human beings, spread across dozens of countries, spending decades of their careers building instruments and writing code, and checking each other's work, all to answer a single question. How fast is the universe expanding? Not because the answer has any practical consequence for human life, not because it will cure disease or generate energy or feed the hungry, but because it matters to know, because the universe is comprehensible, at least in part, and the urge to comprehend it is one of the deepest and most persistent features of the human mind. Because a 6% discrepancy between two measurements of a single number has the power to reshape our understanding of everything. The age of the cosmos, the nature of its dominant energy component, the validity of its most successful theoretical framework. That discrepancy sits there still, patient and unyielding. 8 sigma, 6 kilometers per second per megaparsec, a gap that refuses to close, and into that gap, the most powerful instruments ever aimed at the sky are now pouring their light. The light arrives in pulses that span years. A photon leaves a distant supernova, travels for 8 billion years through the expanding void, and lands on a detector the size of a dinner plate orbiting 600,000 miles from Earth. Another photon, emitted from a Cepheid variable in a galaxy 40 million light-years away, completes its journey in a mere eye blink of cosmic time, 40 million years, and finds its way to a mirror in Arizona or Chile or Hawaii. Each photon is a messenger. Each one carries information about the universe it traversed, and we're only now learning to read the messages properly, to disentangle the news from the noise, to hear what the cosmos has been trying to tell us for as long as there have been ears willing to listen. The Hubble tension is not merely a problem to be solved, it is a question the universe is asking us, and the question is this: do you understand me as well as you think you do? For most of the 20th century, the honest answer would have been no, and cosmologists knew it. The distances were too uncertain, the measurements were too crude, the theoretical framework was a rough sketch, not a detailed map. But somewhere in the transition from the old millennium to the new, something changed. The measurements became precise, the framework became predictive, the rough sketch filled in with exquisite detail, and suddenly the answer seemed to be yes. We understand. We have a model. 6 parameters, billions of data points, predictions that match observations to fractions of a percent. We have cracked the code. The Hubble tension is the universe's gentle correction. Perhaps you have cracked code, it seems to say, but are you certain it is my code? Consider what it would mean if the tension is real, if neither measurement is wrong, if no systematic error hides in the distance ladder, if no calibration mistake lurks in the cosmic microwave background analysis. Consider what it would mean if both numbers are correct, and the universe simply cannot be described by a single expansion rate in the way we assumed. It would mean that the cosmos we thought we knew, the cosmos of lambda CDM, of constant dark energy, of a smooth transition from deceleration to acceleration, is an approximation, a useful one, a remarkably good one, but an approximation nonetheless, and like all approximations, it breaks down somewhere. Perhaps it breaks down at late times, when dark energy begins to show its true evolving nature. Perhaps it breaks down at early times, when some unknown component we have not yet imagined was shaping the infant universe. Perhaps it breaks down on scales we have not yet probed, where the assumptions of homogeneity and isotropy fray at the edges. This is not a failure of cosmology. This is cosmology working exactly as it should. The measurements are precise enough to reveal the cracks. The theory is developed enough to feel the strain. The tension is not a sign that something has gone wrong. It is a sign that something is about to go right, that we are on the verge of learning something genuinely new, something that decades of previous measurements were too imprecise to teach us. But here is the part that keeps cosmologists awake at night, the part that sits beneath all the technical discussions of Cepheid calibrations and CMB power spectra. The part that makes this particular crisis feel different from the ones that came before. We do not know which direction the answer lies. When the evidence for dark energy first accumulated in 1998, the direction was clear within a few years. 2 independent teams measuring supernova distances came to the same conclusion. The universe was accelerating. The physics community was shocked, but the evidence pointed in a single direction, and the task became understanding what could cause such acceleration. Lambda, the cosmological constant, was the simplest explanation, and it fit the data beautifully. But the Hubble tension does not point in a single direction. It points in too many directions at once. Early dark energy could explain it, but so could evolving dark energy, or modified gravity, or new particles, or local voids, or systematic errors, or some combination we have not yet imagined. The space of possibilities is vast, and the data we have so far are not sufficient to collapse it. The tension tells us something is wrong, but it does not tell us what. This is why the next decade matters so much. This is why DESI is mapping millions of galaxies, and Euclid is surveying the sky, and Roman is preparing to launch, and Rubin is readying its camera. not because any single instrument will provide the answer, but because together, converging from different angles with different techniques, they might finally narrow the space of possibilities until only one direction remains, or they might widen it. They might find that the universe is stranger than any of the current alternatives suggest. They might discover disagreements between the new datasets that reveal yet more cracks in the foundation. This, too, would be progress. A map that accurately shows the location of the cliffs is more useful than one that pretends the terrain is smooth. Let me try once more to give you a feel for the stakes. If lambda CDM is correct in its essentials, if the Hubble tension is ultimately resolved by finding a systematic error in one of the measurements, then we will have confirmed that our understanding of the universe is complete in its broad strokes. The details will continue to be refined for centuries, but the basic framework, the 6-parameter model that describes the cosmos from the first fraction of a second to the present day, will have survived its most serious challenge. Cosmology will settle into a period of consolidation, filling in the gaps within an established paradigm. But if the tension is real, if new physics is required, then the settle period is over before it properly began. The 6-parameter model becomes a 7-parameter model, or an 8-parameter model, or something qualitatively different. Dark energy becomes not a constant but a variable, not a fixed feature of space-time but a dynamic field evolving through cosmic history. The expansion rate becomes not a single number but a function, changing from era to era in ways we will need to map and understand. The age of the universe, the eventual fate of the cosmos, the relationship between matter and geometry, all of these might need revision. And behind that revision lies the deeper question, the one that haunts physicists even when they do not speak it aloud. If dark energy evolves, why does it evolve in that particular way? If early dark energy existed, what was it made of and why did it disappear? If the universe has features we have not yet imagined, what principles govern those features? We do not have a theory of dark energy. We have a parameter that fits the observations. That parameter, lambda, the cosmological constant, has no deeper explanation within physics as we currently understand it. It simply is. The value it happens to have is, from the perspective of particle physics, absurdly small, smaller by a factor of 10 to the 120th power than the naive expectation. This is the cosmological constant problem, and it has resisted solution for decades. But as long as the observations were consistent with a constant, cosmologists could at least hope that some deep principle not yet discovered would eventually explain why that particular constant and no other. If dark energy evolves, that hope evaporates. Now we need to explain not just a single absurd value, but an entire trajectory. Why dark energy behaves one way in the early universe, another way in the late universe, and transitions between them in some particular fashion. The puzzle does not simplify. It multiplies. And yet, this multiplication of puzzles might be exactly what physics needs. Sometimes progress requires problems. Sometimes the path forward is visible only when the obstacles are clearly marked. For decades, cosmology has advanced by constructing ever more precise tests of an established model. The Hubble tension is an invitation, perhaps a demand, to advance by a different route, to explore, to speculate with calculations, to build instruments that test ideas rather than merely confirming them. This is the landscape that opens before us now. The tension has not resolved. The measurements have not converged. The alternatives have not been ruled out. And the observers keep observing, patient and meticulous, accumulating the data that will eventually decide. Stop and feel the weight of that for a moment. The fate of a theoretical framework that describes the entire observable universe, 14 billion years of cosmic history, hundreds of billions of galaxies, the vacuum energy that fills all of space, depends on measurements that are still being taken, on photons that are still in flight, on instruments that are still being calibrated. The answer is out there in the data, but the data are not yet complete. We are living in the gap, in the tension, in the uncertainty. The question has been asked, but the universe has not yet finished answering. There is a particular kind of humility required to do cosmology in this moment. Not the false humility that denies the remarkable achievements of the field. Lambda CDM is a triumph, and its predictions have been confirmed to extraordinary precision. but a genuine humility about the limits of that triumph. We know less than we thought we knew. The universe is more surprising than we expected. The discord between two measurements of a single number has revealed that our model, for all its successes, is incomplete. And this incompleteness is not a failure. It is an invitation. The crack in the foundation is not a flaw. It is a doorway. Through it, if we are careful and patient and lucky, we might glimpse something new. Something that transforms cosmology the way dark energy transformed it in 1998. Something that makes the current confusion look, in retrospect, like the first hint of a revolution. Picture the astronomers again. It is late, and the telescope is tracking a Cepheid variable in a galaxy so distant that the light left before multicellular life existed on Earth. The photons arrive one by one, sparse and precious, and the detector counts them through the long night. Somewhere else, on a different continent, a different team is analysing data from a survey of 1 million galaxies, looking for the subtle imprint of sound waves frozen into the distribution of matter. Somewhere else, in a clean room bathed in yellow light, engineers are testing the sensors that will fly on the next space telescope. Somewhere else, on a blackboard in a quiet office, a theorist is working through the mathematics of a dark energy field that evolves with time, checking whether the equations predict something that could be measured. They are all working on the same problem. They are all measuring the same universe, and they are all, in their different ways, trying to hear what the cosmos is telling them. The Hubble tension began as a curiosity, became a crisis, and now stands as something else, a threshold. On one side lies the cosmology we know, the 6-parameter model that has served so well. On the other side lies something unknown, something glimpsed only through the fog of imprecise measurements and speculative models. We cannot yet see what is there. We can only see that there is something, 8 sigma, 6 kilometers per second per megaparsec, the gap that will not close. Some gaps are errors waiting to be found. Some gaps are features of nature, irreducible truths that no amount of calibration will erase. The art of science lies in telling the two apart. That art takes time. It takes patience. It takes instruments that have not yet been built and observations that have not yet been made. It takes the slow accumulation of evidence, each piece uncertain on its own, each piece valuable only in the context of the others. But the art is being practiced. Right now, as you listen, photons are falling on detectors and bits are streaming from satellites, and theorists are checking their calculations. The work continues. The question remains open. And the universe, vast and dark and cold, expands outward at a rate we still cannot quite measure. There will come a day, perhaps in 5 years, perhaps in 10, perhaps in 20, when the Hubble tension resolves. When the converging lines of evidence finally cross and the answer becomes clear. When cosmologists can say, with confidence, whether the discrepancy was systematic error or new physics, whether lambda CDM survives intact or requires fundamental revision, whether dark energy is constant or evolving, whether the universe is the universe we thought or something stranger. That day has not arrived. We are still in the middle of the story, still uncertain, still measuring. The ending has not been written. But the ending is coming. The instruments are watching. The data are accumulating. And somewhere in the flood of numbers, the answer is already there, hidden, waiting, patient as the light that has been travelling since the universe was young. What we do know is this. 2 numbers disagree. The disagreement is real, and the universe does not care what we expected. The cosmic microwave background, that ancient light from the surface of last scattering, tells us that the universe should be expanding at 67 kilometers per second per megaparsec. Every feature of that primordial glow, every peak and trough in its power spectrum, every subtle pattern in its polarization points to that number. The physics of the early universe, as we understand it, demands that number. The distance ladder, the chain of standard candles reaching from Earth to the most distant galaxies, tells us that the universe is expanding at 73 kilometers per second per megaparsec. Every Cepheid variable, every type Ia supernova, every measured redshift and luminosity distance points to that number. The physics of stars and gravity and light, as we understand it, demands that number. Both numbers cannot be right, and neither number will yield. This is the Hubble tension. This is the discord that has troubled cosmology for nearly a decade. This is the crack in the foundation, the whisper in the data, the question the universe is asking, that we do not yet know how to answer. But listen to what it is really saying. It is saying that the universe is more than we have measured. It is saying that our instruments, for all their precision, have not captured everything. It is saying that somewhere in the fabric of reality there is a feature we have missed, a connection we have overlooked, a piece of the puzzle we have not yet picked up. The tension is not a wall, it is a window. Through it, we might see the next chapter of cosmology. The chapter after lambda CDM, after the concordance model, after the era when 6 parameters seemed sufficient to describe all of creation. That chapter has not been written, but the first sentences are already there, encoded in the disagreement between 2 measurements of a single number, and the measurements continue, in observatories on mountaintops and in satellites drifting through space, in data centers humming with the analysis of 1 billion galaxies, in the quiet work of astronomers who have dedicated their careers to making distances just a little more precise, systematics just a little better understood, uncertainties just a little narrower. They are not looking for glory. They are not looking for a Nobel Prize. They are looking at the sky, the way human beings have looked at the sky for 100,000 years, and they are asking the oldest question, what is out there? The answer, it turns out, is stranger than we expected. The universe is expanding, and we cannot quite agree on how fast. 2 methods, both excellent, both refined over decades, both applied with care and rigour and humility, give different answers. The disagreement is precise, it is reproducible, and it will not go away. Somewhere in that disagreement lies the future of cosmology. Somewhere in the gap between 67 and 73 lies a truth we have not yet grasped. It might be a truth about dark energy, that the vacuum is not constant, that the cosmos is evolving in ways we have only begun to imagine. It might be a truth about the early universe, that something we have not yet named shaped the primordial plasma before the first atoms formed. It might be a truth about our methods, that one of the measurements, for all its precision, contains an error we have not yet found. We do not know, not yet, but we are looking, we are measuring, we are building the instruments and doing the calculations and checking each other's work. This is how the answer will come. Not in a flash of insight, but in the slow, patient accumulation of evidence. 1 photon at a time, 1 galaxy at a time, 1 decimal place at a time. The universe expands, the light travels through the void. The instruments wait, patient and precise, for the photons that will tell us the truth, and we wait with them. The dark is vast. The distances are immense. The cosmos stretches outward in every direction, carrying its galaxies like islands on an ocean with no far shore. And somewhere in that darkness, the answer to the Hubble tension is already written, in the distribution of matter, in the behaviour of light, in the fundamental constants that govern all of creation. We have asked the question. The universe is answering. We need only listen long enough to hear. The tension remains, the gap persists, and the measurements continue, as they have continued for a century now, reaching ever deeper into the cosmic dark, ever further back toward the beginning of time, ever closer to the truth that hides behind the numbers, 67, 73, 2 measurements, 2 universes, 1 cosmos. Somewhere between them, reality waits to be understood. The light keeps falling, the detectors keep counting. And in observatories around the world and in satellites drifting through the silence of space, the question hangs in the air like the last note of a symphony that has not yet resolved. How fast is the universe expanding? We have measured and measured again with instruments of increasing power and methods of increasing subtlety. We have checked and rechecked, calibrated and recalibrated. We have argued over systematics and debated over priors and published paper after paper in journals that only a few thousand people on Earth will ever read. And still the numbers disagree. This is where we are. This is where cosmology stands in the 3rd decade of the 21st century. Not in triumph, though there is much to celebrate. Not in defeat, though there is much we do not understand. But in tension, in the productive, uncomfortable, necessary tension between theory and observation, between what we expected and what we found. The universe is not obligated to be simple. It is not required to fit our models. It is what it is, and our task is merely to measure it as accurately as we can, to build theories that explain what we observe, and to follow the evidence wherever it leads, even when it leads to places we did not expect, even when it reveals that our most successful frameworks are incomplete. The Hubble tension leads to such a place. We do not yet know what waits there, but we are walking toward it, step by careful step, measurement by patient measurement. And perhaps that is the most important thing to understand. Not the answer, we do not have the answer, but the process. The careful, methodical, stubborn process of science at the frontier. The willingness to be wrong, the insistence on checking, the patience to let the data accumulate until the truth emerges on its own. The universe is 14 billion years old. It contains 2 trillion galaxies. It is expanding into a future we cannot see, carrying all of us along with it. And we are still learning how fast. Let the numbers sit with you. 67, 73. 2 precise measurements of a single cosmic truth that refuse to agree. In that disagreement lives a mystery. Perhaps the greatest mystery in contemporary physics. Not because the numbers are large, but because they are so carefully measured. Not because we do not know enough, but because we know almost enough. We are close, so close. And the last step is always the hardest. The Hubble tension is that last step. Or perhaps it is the first step into a new territory, a new cosmology, a new understanding of the universe we inhabit. We do not know which, not yet, but the measurements continue, the light keeps falling, and somewhere out there, in the vast and patient dark, the answer waits.